Welcome. Friends, I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the story of a comet that arrived late, not by minutes, but by hours measured across the emptiness of space, and what that delay revealed about ice, light, and the sun's patient influence on bodies born under other stars. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The comet does not know it is moving. It has no awareness of velocity or direction, no sense of the sun growing brighter in what might be called a head. For millions of years it has traveled through the space between stars, a frozen nucleus of water ice and carbon compounds and silicate dust, 3 kilometers across, tumbling slowly through a darkness so complete that the Milky Way itself appears as little more than a faint smear of collected starlight. The comet is cold. Not the cold of winter or high altitude, but cold measured at tens of degrees above absolute zero, the temperature at which molecular motion nearly ceases, where gases freeze solid and time itself seems to slow. It is designated 3I/Atlas, the third confirmed interstellar object detected passing through the solar system. The I denotes its origin, interstellar, meaning it did not form in orbit around the sun, but elsewhere, in the planetary debris disk of a star whose light has never been identified. Somewhere, decades or centuries or millennia ago, this small body was ejected from its home system, perhaps by the gravitational influence of a giant planet, perhaps by a close stellar encounter. It was cast out, and it has been falling ever since, one small ice-clad stone among trillions, invisible and unremarkable, until the sun's gravity begins to curve its path. The change is gradual. At first, the deflection is so slight that it would take years of observation to detect, but gravity does not tire. The sun, though still a faint point among the background stars, exerts its influence across light years, a gentle but inexorable pull that begins to reshape the comet's trajectory from a nearly straight line into a hyperbolic curve. The comet falls inward. Astronomers detect it first as a faint smudge on survey images, a moving point of light that does not follow the expected orbit of any known asteroid or comet. When orbital calculations are run, the numbers do not fit any elliptical path around the sun. The eccentricity is greater than 1, a hyperbolic orbit, meaning the object is not bound to the solar system at all. It is passing through. The comet is moving at a speed that indicates an origin far beyond the heliopause, beyond the scattered disk, beyond the Oort cloud's outermost theoretical boundary. It came from interstellar space, and now it is falling toward the sun. The distance between them shrinks steadily, day by day. The comet crosses the orbital distance of Neptune, then Uranus, each planetary orbit marking a threshold of increasing solar influence. At these distances, the sun is still only a bright star, offering almost no warmth, but its light is enough. Photons travel outward and strike the comet's surface, a surface that has been dark and cold for longer than human civilization has existed. The ice begins to absorb energy, not much, a few watts per square meter, spread across the irregular, rotating nucleus. The surface warms, slowly, from perhaps 20 Kelvin to 30, then 40. The comet tumbles as it falls, its rotation axis tilted at some arbitrary angle, so that different regions of the surface receive sunlight in turn. Some areas, facing the sun for prolonged periods, warm faster, others, shadowed or facing away, remain cold. This creates thermal gradients, stress within the ice, microscopic fractures that propagate slowly through the crystalline structure. At some point, no one can say exactly when, water ice near the surface begins to sublimate, not melt. There is no liquid phase here. Instead, the ice transforms directly from solid to vapor, molecules breaking free from the crystalline lattice and escaping into the vacuum. The escaping water vapor carries away energy, but also carries with it tiny grains of dust, particles of silicate and organic carbon that were mixed into the ice when the comet first formed. Perhaps 4.5 billion years ago, perhaps longer. The comet begins to develop a coma. At first, the coma is invisible, too faint to detect. It consists of a thin haze of water vapor and other volatiles, carbon monoxide, carbon dioxide, methane, expanding outward from the nucleus at speeds of a few hundred meters per second. The molecules move in ballistic trajectories, subject only to the sun's radiation pressure and the gentle tug of the comet's own minuscule gravity. Some molecules escape entirely. Others fall back to the surface, redepositing as frost in shadowed regions. Dust grains, carried along with the vapor, form a separate component of the coma. The dust reflects sunlight directly, making the coma visible as a faint, diffuse cloud surrounding the nucleus. The dust particles are small, most are only micrometers across, and they are pushed outward by radiation pressure. The result is a sorted distribution, with the finest dust forming the outer reaches of the coma and larger particles concentrated near the center. The coma grows. Within weeks, it expands to tens of thousands of kilometers, then hundreds of thousands. By the time the comet crosses the orbital distance of Mars, the coma is larger than the planet itself, though still so tenuous that the total mass of gas and dust within it amounts to perhaps a few million kilograms. The nucleus itself remains invisible, hidden within the brightening haze. And then the calculations begin to drift. Orbital mechanics is a precise science. Given a body's position and velocity at any moment, and accounting for the gravitational influence of the Sun and major planets, one can predict its future trajectory with extraordinary accuracy. But active comets do not follow the predictions exactly. The escaping gas acts as a rocket engine, exerting a small but measurable thrust on the nucleus. If the outgassing is asymmetric, if more gas escapes from one side than the other, the comet experiences a net force that alters its trajectory. This is called a non-gravitational force, for 3I/Atlas. The non-gravitational force is small but not negligible. As the comet approaches perihelion, the point of closest approach to the Sun, astronomers refine their predictions. But as the comet draws nearer, a discrepancy appears. The comet is not arriving when it should. The difference is small, minutes at first, then tens of minutes, then hours, but it is real and measurable. The comet is late, not late in any human sense, but late according to the mathematics of gravity. The delay is caused by the outgassing, by the thrust of subliming ice acting like a retro rocket, slowing the comet's forward motion by a tiny fraction. By the time perihelion approaches, the comet's arrival time has shifted by several hours. Only took a few million kilometers of travel to notice. The delay is a kind of clock, a measure of how much ice is subliming, how active the comet truly is. For 3I/Atlas, the delay provides information that cannot be obtained any other way, information about the interior composition, the distribution of ice and rock, the way heat propagates through the nucleus. The comet does not know it is being measured. It simply sublimates, tumbles, and falls, while human instruments track its position and recalculate, again and again. The orbit that is no longer quite what it was. The Sun continues to brighten ahead. The mathematics of celestial mechanics rests on a foundation laid centuries ago, when Newton described gravity as an inverse square force, a pull that weakens with distance but never entirely disappears. Given the mass of the Sun and the position and velocity of any orbiting body, the future path can be calculated with precision that seems almost prophetic. Astronomers in the 18th century used these equations to predict the return of comets decades in advance, to discover planets by the perturbations they caused in their neighbors' orbits, to map the clockwork motions of moons around Jupiter with such accuracy that their eclipses could be used to measure longitude at sea. The equations work. They describe reality with a fidelity that borders on the uncanny. But they describe only gravity. For 3I/Atlas, the initial orbital determination relies on observations made when the comet is still far from the Sun, still cold, still inactive. At these distances, beyond the orbit of Jupiter, where sunlight is weak and surface temperatures hover near the ambient cold of deep space, the comet behaves like an inert rock. It follows a purely gravitational trajectory, curving smoothly through space according to Newton's laws, later refined by Einstein's general relativity to account for the subtle warping of space-time near massive bodies. The observations accumulate each night. Telescopes image the comet's position against the background stars, measuring its right ascension and declination to fractions of an arcsecond. The data points are fed into orbit-fitting algorithms that solve for the 6 orbital elements: semi-major axis, eccentricity, inclination, longitude of ascending node, argument of perihelion, and time of perihelion passage. The solution converges. The comet's orbit is hyperbolic. As expected for an interstellar visitor, the eccentricity is approximately 1.3, meaning the trajectory is open, unbound. The comet will pass through the solar system once and continue outward, never to return. The perihelion distance is calculated at roughly 0.6 astronomical units, well inside Earth's orbit, closer to the Sun than Venus. The inclination is steep, nearly perpendicular to the plane of the planets, which is consistent with an object that formed in a different stellar system and entered the solar system from an arbitrary direction. And the time of perihelion passage, the moment when the comet will reach its closest approach to the Sun, is predicted with what seems like certainty: a specific date, a specific hour, based on the assumption that only gravity matters. At first, the assumption holds. The comet's position, measured night after night, matches the predicted ephemeris within the expected uncertainties. The orbital model is validated. Confidence grows. Observers plan their campaigns around the predicted perihelion date, scheduling telescope time, coordinating spacecraft observations, preparing instruments to capture the comet at its brightest and most active. The mathematics says the comet will be here, at this position in the sky, at this moment in time, and for weeks. The comet obliges. Then the comet crosses the orbit of Mars. The change is not immediate. It accumulates slowly. A small discrepancy that appears first as a systematic offset in the residuals, the difference between observed and predicted positions. At first, the offset is within the noise, attributable to measurement error or slight inaccuracies in the positions of reference stars. But as more observations are added, the pattern becomes clear. The comet is consistently behind where it should be, not by much, only a few arcseconds on the sky, corresponding to a few thousand kilometers in space, but the trend is unmistakable. The comet is arriving late. Astronomers recognize the signature immediately. This is the effect of non-gravitational forces, specifically the rocket effect caused by asymmetric outgassing. As the comet's surface warms and ice begins to sublimate, gas molecules escape into space, carrying momentum with them. If the nucleus were a perfect sphere rotating uniformly, and if the ice were distributed evenly across the surface, the outgassing would be symmetric and the forces would cancel. But comets are not perfect spheres. They are irregular, often elongated or lumpy. with surfaces that vary in composition and albedo. Some regions are richer in volatile ices, others more dusty or rocky. The rotation axis is tilted at some arbitrary angle, and the rotation period may be hours or days, creating a complex pattern of heating and cooling as different parts of the surface rotate into and out of sunlight. The result is that outgassing is strongest on the sun-facing side, particularly in the hours after local noon, when the surface has had time to warm but is still receiving direct sunlight. This creates a net force, a thrust that acts like a rocket engine firing in a specific direction. If the comet is rotating in such a way that the outgassing occurs preferentially in the direction opposite to the comet's motion along its orbit, what is called a retrograde force, the comet will slow down. It will take longer to reach perihelion than the purely gravitational model predicts. Conversely, if the outgassing produces a prograde force accelerating the comet along its path, it will arrive early. For 3I/Atlas, the delay indicates retrograde thrust. The comet is slowing down. Not by much. The acceleration is only a few millimeters per second squared, a tiny fraction of the sun's gravitational pull, but sustained over weeks and months. It adds up. The velocity deficit accumulates. By the time the comet is a few weeks from perihelion, the arrival time has shifted by minutes, then tens of minutes, then hours. The orbit must be recalculated. New models are developed that include non-gravitational forces. These models are more complex than the purely gravitational ones, requiring additional parameters to describe the magnitude and direction of the outgassing thrust. The simplest approach assumes the thrust is radial, directed either toward or away from the sun, and proportional to some inverse power of the comet's distance from the sun. Reflecting the fact that sublimation increases as the comet warms, more sophisticated models account for the rotation of the nucleus, the thermal inertia of the surface, the lag between maximum heating and maximum outgassing. But even the simple models improve the fit significantly. The residuals shrink. The predicted positions match the observed ones more closely, and the new perihelion time is later. Hours later. This is not a failure of the mathematics. The equations of motion are still correct. They simply need to include all the forces acting on the comet, not just gravity. The delay is real. It is a physical consequence of the comet being active, of ice transforming into gas and escaping into space. It is, in a sense, the comet announcing its presence not just as a gravitational object, but as a dynamic, evolving body responding to the sun's heat. Only took crossing half the solar system to need an update. The recalculated orbit carries its own uncertainties. The non-gravitational force is not constant. It varies with the comet's distance from the sun, with the rotation phase, with changes in the active area as surface ice is depleted or fresh ice is exposed by fragmentation. Predicting these variations requires knowledge of the comet's interior structure, composition, and thermal properties, information that is not directly observable, so the models are refined iteratively, adjusting the parameters as new observations come in, updating the predictions day by day. The perihelion time shifts slightly with each update, converging toward a value that reflects the best current understanding of the comet's behavior. But there is an irreducible uncertainty. Even with perfect observations and perfect models of outgassing, the comet's future trajectory cannot be predicted with the same precision as an inert asteroid. The comet is too active, too variable, too responsive to forces that are themselves difficult to predict. The mathematics can describe the average behavior, the general trend, but not the exact moment of perihelion to the minute. There is a fundamental limit to predictability when a body is actively shedding mass and changing its own orbit in the process. This is not unique to 3I/Atlas. Every active comet exhibits non-gravitational forces. Short-period comets like Halley's Comet have been studied for centuries, and their orbits are well characterized. But even Halley's perihelion time cannot be predicted decades in advance to better than a few hours. Each apparition brings surprises, outbursts, fragmentation events, changes in rotation that alter the orbit in ways that were not anticipated. The comets do not follow the pure mathematics of gravity. They are governed also by thermodynamics, by the phase transitions of ice, by the mechanical strength of their nuclei and the way heat diffuses through porous, insulating dust, and 3I/Atlas. Coming from interstellar space carries additional mysteries. Its composition may differ from solar system comets, reflecting the chemistry of a different protoplanetary disk, a different mixture of ices and organics and silicates. Its ice may be more or less volatile. Its dust-to-gas ratio may be higher or lower. Its response to solar heating may be stronger or weaker than expected based on observations of comets born here. The delay in arrival time is one of the few direct measurements of these properties, a clue embedded in the discrepancy between prediction and observation. The comet continues to fall. The sun grows brighter, warmer, more insistent. The coma expands. The outgassing intensifies. And the orbit, recalculated again and again, converges toward a new perihelion time, a time that is still uncertain, still shifting slightly with each new set of observations, but closer to the truth than the original prediction. The mathematics adapts, the comet does not. Sublimation is a betrayal of sorts. Though the word implies intent where none exists, the ice does not choose to transform. It simply obeys the laws of thermodynamics, responding to the influx of solar radiation by transitioning from solid to vapor without passing through the liquid phase. This process, common enough on Earth with dry ice or frost on a winter morning, occurs continuously across the comet's sunlit hemisphere as it approaches perihelion. Water molecules, locked in crystalline lattice structures for billions of years, absorb enough energy to break free from their neighbors and escape into the vacuum of space. The transition is quiet. There is no sound, no visible indication beyond the slow brightening of the coma, just molecules departing, one by one, at velocities of a few hundred meters per second. The rate of sublimation depends on temperature, which in turn depends on distance from the sun, the angle of incident sunlight, the albedo of the surface, and the thermal inertia of the material. Ice in direct sunlight warms faster than ice in shadow. Dark, dusty regions absorb more energy than bright, clean ice. Porous material, filled with tiny voids and gaps, insulates the subsurface, creating a temperature gradient that slows the conduction of heat downward. The result is that sublimation is not uniform across the nucleus. It is concentrated in certain areas, the subsolar point, where sunlight strikes most directly, equatorial regions, which receive prolonged illumination as the nucleus rotates, fresh ice exposures, where recent fractures or fragmentation have removed the insulating dust layer. These active areas become jets, localized sources of outgassing that produce higher gas densities and velocities than the surrounding regions. Spacecraft observations of other comets have revealed these jets as bright plumes extending from the nucleus, visible in images taken at high resolution. The jets are not steady. They turn on and off as the nucleus rotates, as active regions move into and out of sunlight, as surface ice is depleted or covered by dust. Some jets are short-lived, lasting only hours or days. Others persist for weeks, fed by subsurface reservoirs of ice that remain active even as the surface layer is exhausted. For 3I/Atlas, the jets are invisible at the distance of Earth-based telescopes, too small and faint to resolve, but their presence is inferred from the non-gravitational forces, from the way the outgassing alters the orbit. The direction of the thrust provides clues about the location of the active areas. A purely radial force, directed straight away from the sun, suggests symmetric outgassing, with jets distributed evenly across the sunlit hemisphere. A transverse force, perpendicular to the Sun-comet line, suggests asymmetry, with jets preferentially located on one side of the nucleus or oriented at an angle to the radial direction. The magnitude of the force indicates the total mass loss rate, the amount of gas and dust being ejected per unit time. The mass loss is substantial. At perihelion, when the comet is closest to the Sun and the surface temperature peaks, the sublimation rate may reach tens of kilograms per second, perhaps more. Over the course of hours or days, this amounts to millions of kilograms of material lost, ice transformed into vapor, dust grains liberated and carried away by the expanding gas. For a nucleus only 3 kilometers across, this is a significant fraction of the total mass. If the comet were pure ice, with no rocky or dusty component, it might lose a measurable percentage of its mass during a single perihelion passage. But comets are not pure ice. They contain dust, silicates, organic compounds, non-volatile material that remains behind as the ice sublimates, forming a porous, crumbly layer on the surface called a mantle. The mantle builds up over time, insulating the underlying ice and reducing the sublimation rate. If the mantle becomes thick enough, it can shut off outgassing entirely, rendering the comet inactive even when it is close to the Sun. But mantles are fragile. They can be disrupted by thermal stress, by the pressure of gas escaping from below, by impacts from small meteoroids, or by the mechanical forces associated with rotation. When the mantle cracks or breaks away, fresh ice is exposed and sublimation resumes, sometimes explosively. These outbursts, sudden increases in brightness and gas production, are common among comets and are thought to be caused by the catastrophic failure of a dust mantle or the exposure of a volatile-rich pocket within the nucleus. 3I/Atlas has not yet experienced an outburst, at least not one large enough to be detected from Earth. The brightening has been steady, predictable, consistent with gradual warming and increasing sublimation as the comet approaches the Sun, but the potential remains. Somewhere within the nucleus, there may be regions of pure ice, pockets of carbon monoxide or other highly volatile compounds, fractures filled with pressurized gas waiting for a pathway to the surface, if such a region is suddenly exposed by a rockfall, a thermal crack, a rotational stress. The comet could brighten dramatically, releasing a plume of gas and dust that would alter the coma's appearance and perhaps the orbit itself, or the nucleus could fragment. Fragmentation is common among comets, particularly those making close approaches to the Sun. The mechanisms are not fully understood, but thermal stress is thought to play a significant role. As the surface heats and cools with the rotation of the nucleus, and as sublimation removes material unevenly, stresses build within the ice. The nucleus may already be fractured from previous perihelion passages if this is not the comet's first encounter with a star, or from collisions in its distant past. These pre-existing fractures act as weak points. When the stress exceeds the tensile strength of the ice, the nucleus splits apart, each fragment becoming a separate comet with its own coma and trajectory. The fragments do not separate quickly. They drift apart at speeds of only meters per second, remaining gravitationally unbound but close enough that their comae overlap and merge. From a distance, the comet may appear as a single diffuse cloud, but high-resolution observations reveal multiple condensations, bright knots within the coma marking the positions of individual fragments. Over days or weeks, the fragments spread along the orbit, forming a train of debris that gradually disperses. Some fragments are large enough to survive for months or years. Others, too small or too fragile, disintegrate within hours, their material absorbed into the coma and lost. For 3I/Atlas, the risk of fragmentation increases as perihelion approaches. The thermal stress will peak at closest approach. when the solar flux is highest and the temperature gradients are steepest. If the nucleus is structurally weak, if it is a loose aggregate of smaller pieces held together by ice rather than a single coherent block, it may not survive. The outgassing itself could provide the final push. The pressure of escaping gas overcoming the weak cohesive forces and breaking the nucleus into pieces, or the rotation, if it is rapid enough, could generate centrifugal forces that exceed the material's strength. Only took a few billion years to find out if it holds together. The uncertainty is part of what makes comets difficult to predict. Unlike asteroids, which are solid and stable, comets are dynamic, fragile, constantly changing in response to solar heating. Each comet is different, with its own unique composition, structure, and evolutionary history. Some survive multiple perihelion passages with minimal change. Others fragment on their first approach or disintegrate entirely, leaving nothing behind but a dispersing cloud of dust. There is no way to know in advance which outcome will occur. The only option is to observe, to watch as the comet approaches and responds to the sun's warmth, and to see whether the nucleus endures or breaks apart. The jets continue. The gas escapes, the dust is carried away, and the nucleus, hidden within the growing coma, rotates and warms and sublimates, shedding mass at a rate that cannot be sustained indefinitely. The comet is consuming itself, transforming its own substance into the ephemeral beauty of the coma and tail. This is the quiet betrayal, not of trust or loyalty, but of permanence. The ice that has traveled so far, that has survived so long in the cold of interstellar space, is now being destroyed by the very light it has fallen toward. The sun gives warmth, but warmth is corrosive here. It unmakes the comet molecule by molecule, leaving behind only dust and vapor and the slowly diminishing core. The coma, by the time the comet crosses Earth's orbital distance, has expanded to a diameter exceeding 400,000 kilometers, larger than the planet Jupiter, larger than the distance between Earth and the Moon. This vast cloud is almost entirely empty space. If all the gas and dust within the coma were compressed to the density of Earth's atmosphere at sea level, it would occupy a volume no larger than a small building. The particles are so widely dispersed that a spacecraft could fly through the coma and have only a small chance of striking a dust grain larger than a millimeter. Yet, from a distance, the coma appears solid, a glowing sphere that brightens and dims as the rate of outgassing varies with the nucleus's rotation and distance from the sun. The glow comes from two sources. The dust reflects sunlight directly, scattering photons in all directions and giving the coma a yellowish or white appearance similar to sunlight itself. The gas, by contrast, fluoresces. Ultraviolet photons from the sun strike gas molecules in the coma: water, carbon monoxide, cyanogen, diatomic carbon, exciting electrons to higher energy states. When the electrons fall back to their original states, they emit photons at specific wavelengths, creating an emission spectrum that is characteristic of the molecular composition. Water vapor emits in the ultraviolet, cyanogen emits a greenish light, carbon monoxide emits in the ultraviolet and visible. By analyzing the spectrum of the coma, astronomers can determine which molecules are present and in what abundances. Providing a chemical fingerprint of the comet's interior, the nucleus itself, still only 3 kilometers across, remains invisible within the coma. It is too small to resolve in telescopes from Earth, too dark to stand out against the brighter surrounding gas and dust. Even if the coma were removed, the nucleus would be faint. Its surface is likely as dark as charcoal, reflecting only a few % of incident sunlight, similar to other cometary nuclei that have been observed up close by spacecraft. This low albedo is caused by the organic compounds mixed into the ice, carbon-rich molecules that absorb light across most wavelengths. The surface may be covered by a layer of dust, the residue left behind as ice sublimates, further darkening the appearance and reducing the reflectivity. But the nucleus is there, at the center of the expanding cloud, rotating and sublimating and gradually losing mass. Its gravity is negligible. An object on the surface would weigh only a few grams, barely enough to keep it from floating away, but gravity is not what holds the nucleus together. The cohesive forces are mechanical. The strength of the ice itself and the weak bonds between ice grains in what is likely a porous, fluffy structure rather than a solid block. The bulk density of cometary nuclei, measured for those few comets that have been visited by spacecraft, is typically less than half that of water ice, indicating that the interior is filled with voids and gaps, a fragile architecture that could collapse under its own weight if it were any larger. The rotation period has been estimated from variations in the coma's brightness. Though the signal is weak and the period is uncertain, the nucleus appears to rotate once every several hours, possibly 8 to 12 hours, though this could be the period of a complex tumbling motion rather than a simple spin. The rotation axis is oriented at some unknown angle to the orbital plane, and the shape of the nucleus is also unknown. It could be elongated, bilobed, irregular, or relatively spherical. These unknowns limit the precision of models that attempt to predict the outgassing pattern and the resulting non-gravitational forces. Without knowing the shape and rotation, it is difficult to determine where on the surface the active areas are located or how they will evolve as the comet approaches perihelion. The coma expands at velocities determined by the thermal speed of the gas molecules. Water vapor, at a temperature of around 200 Kelvin, moves at roughly 500 meters per second. Carbon monoxide, being lighter, moves faster, around 700 meters per second. These velocities are much higher than the escape velocity from the nucleus, which is only about 1 meter per second. So nearly all the gas that sublimates escapes entirely, carrying dust with it. The gas moves radially outward from the nucleus, expanding in all directions. Though the expansion is slightly faster on the sunward side where the outgassing is strongest, as the gas expands, it cools. The molecules, initially near the surface temperature of the ice, lose energy through collisions with other molecules and through the work done in expanding against the sun's radiation pressure. By the time the gas has traveled a few thousand kilometers from the nucleus, its temperature has dropped to perhaps 50 Kelvin or less, and the density is decreased to the point where collisions are rare. The gas then moves ballistically, each molecule following its own trajectory without further interaction with its neighbors. This transition from collision-dominated flow near the nucleus to ballistic expansion in the outer coma occurs at a distance that depends on the outgassing rate and the gas composition. Dust particles, embedded in the expanding gas, are carried along by collisions with gas molecules. Near the nucleus, where the gas density is highest, the dust is strongly coupled to the gas and moves outward at roughly the same velocity. But as the gas expands and the density drops, the coupling weakens. Larger dust grains, more massive and less affected by collisions, decelerate and fall behind. Smaller grains, with higher surface area to mass ratios, remain coupled to the gas longer and are carried farther out. The result is a size-dependent distribution, with the smallest particles, submicron grains comparable to smoke, reaching the outer regions of the coma, while larger particles, tens or hundreds of microns, remain concentrated near the nucleus. The dust also experiences radiation pressure, the momentum imparted by photons striking the particle surface. Radiation pressure is inversely proportional to particle size, so small grains are pushed away from the sun more strongly than large grains. This creates a selective sorting. The smallest grains are accelerated to velocities exceeding the gas expansion velocity and stream away from the nucleus in the anti-sunward direction, forming the dust tail. Larger grains, less affected by radiation pressure, remain in the coma or are slowly pushed outward along a curved path. their motion determined by a balance between the sun's gravity and radiation pressure. The coma is not static. It responds to changes in the outgassing rate as the nucleus rotates and as the distance to the sun varies. When an active area rotates into sunlight, the local outgassing increases, creating a temporary enhancement in the coma brightness. When the active area rotates into shadow, the outgassing decreases and the brightness fades. These variations occur on timescales of hours, matching the rotation period of the nucleus. Longer-term variations, on timescales of days or weeks, are caused by the changing distance to the sun as the comet approaches perihelion. The outgassing rate increases as the solar flux increases, leading to a steady brightening of the coma that will peak at perihelion and then decline as the comet recedes. The expansion continues. The coma grows, and within it, hidden from view, the nucleus continues its slow disintegration, shedding mass at a rate that is now measurable, now significant, now altering the orbit in ways that the original predictions did not anticipate. The cloud is larger than Jupiter, but it is made of almost nothing, a tenuous haze of molecules and particles dispersed across a volume so vast that the average density is lower than the best laboratory vacuum. Yet this near vacuum is enough to scatter sunlight, enough to fluoresce in ultraviolet, enough to make the comet visible across millions of kilometers of space. Only took a few tons of ice to become larger than the largest planet. The coma is the comet's announcement, the visible consequence of processes occurring on a body too small and dark to see. It is both the comet's glory and its demise, a transient structure born from the destruction of the nucleus, beautiful only because it is dying, bright only because it is falling apart. The molecules that make up the coma will continue to expand, dispersing into the solar wind, eventually traveling so far from the nucleus that they are indistinguishable from the background population of neutral atoms and ions that fill interplanetary space. The dust will linger longer, following orbits that may cross Earth's path centuries or millennia hence, burning as meteors in the upper atmosphere. But the coma itself, this vast glowing cloud, exists only for a brief interval, a few weeks or months at most, before the comet moves away from the sun and the outgassing ceases. For now, it continues to grow. Light exerts pressure. This fact, predicted by Maxwell's electromagnetic theory in the 19th century and confirmed experimentally in the early 20th, is a direct consequence of the momentum carried by photons. Each photon, though massless, carries momentum proportional to its energy. And when a photon strikes a surface and is absorbed or reflected, it transfers that momentum to the surface. For everyday objects on Earth, the force is negligible. Radiation pressure from sunlight amounts to only about 9 micronewtons per square meter, far too small to notice against the backdrop of gravity and air resistance. But in space, where gravity is weak and there is no air, radiation pressure becomes significant, particularly for objects with large surface areas and low masses. Dust particles in the comet's coma are ideal targets for radiation pressure. A typical grain, 1 micron in diameter, has a mass of roughly 1 picogram, 1 trillionth of a gram. When struck by sunlight, it experiences a force of about 1 femtonewton, an absurdly small number in absolute terms, but enormous relative to the particle's mass. The resulting acceleration is on the order of 1 millimeter per second squared, sustained continuously as long as the particle remains illuminated. Over hours or days, this acceleration adds up to velocities of meters per second or more, enough to carry the particle away from the nucleus and out of the coma entirely. The direction of the force is radial, away from the sun, because photons travel outward from the sun and push on whatever they strike. This creates a natural sorting mechanism. Particles that are strongly affected by radiation pressure those with the highest surface area to mass ratios. Typically, the smallest grains are accelerated away from the Sun more quickly than particles that are less affected. The result is a size-dependent distribution in the coma and tail, with the smallest particles forming the outermost, fastest-moving components and the largest particles remaining closer to the nucleus. But radiation pressure is not the only force acting on the dust. Gravity from the Sun also pulls on the particles, attempting to curve their trajectories into orbits around the Sun. The balance between radiation pressure and gravity determines the particle's fate. For very small particles, radiation pressure dominates, and the particles are blown out of the solar system entirely, escaping on hyperbolic trajectories. For larger particles, gravity dominates, and the particles remain bound to the Sun, following elliptical orbits that may persist for thousands or millions of years. The transition occurs at a particle size of roughly 1 micron, though the exact value depends on the particle's density and composition. This balance is quantified by a parameter called beta, defined as the ratio of radiation pressure force to gravitational force. For particles with beta greater than 1, radiation pressure dominates and the particles escape. For particles with beta less than 1, gravity dominates and the particles remain bound. Beta depends on the particle size, with smaller particles having higher beta values. A 1 micron grain has a beta near 1. A submicron grain has beta greater than 1. A 10 micron grain has beta around 0.1. The distribution of beta values in the coma reflects the distribution of particle sizes, and by measuring the shape and brightness of the dust tail, astronomers can infer the size distribution of the dust being released from the nucleus. For 3I/Atlas, the dust tail is beginning to form. It is not yet prominent. The comet is still relatively far from the Sun, and the dust production rate is modest. But sensitive observations reveal a faint extension of the coma in the anti-sunward direction, a diffuse fan of scattered light that marks the trajectory of escaping dust grains. The tail is broad and slightly curved, reflecting the range of particle sizes and the variation in their trajectories as they are pushed outward by radiation pressure and pulled inward by the Sun's gravity. The curvature is subtle, a gentle arc that becomes more pronounced with distance from the nucleus as particles with different beta values separate along their diverging paths. The gas in the coma also experiences radiation pressure. Though the effect is weaker than for dust, gas molecules are much smaller than dust grains, and their cross-sections for absorbing or scattering photons are correspondingly smaller. But gas molecules can absorb photons at specific wavelengths corresponding to electronic or vibrational transitions, and when they do, they experience a resonant radiation pressure that can be much stronger than the continuum pressure on dust. This resonant pressure is highly wavelength dependent and occurs only for photons whose energy matches the transition energy of the molecule. Water vapor, for example, absorbs strongly in the ultraviolet, where the Sun's spectrum has significant flux. When a water molecule absorbs an ultraviolet photon, it is excited to a higher electronic state and experiences a recoil, a tiny kick in the direction of the photon's momentum. The molecule then re-emits a photon, often in a different direction, and experiences another recoil. The net effect, averaged over many absorption and emission cycles, is a force that pushes the molecule away from the Sun. This force is smaller than the radiation pressure on dust, but it is not negligible, and it contributes to the overall expansion of the gas coma. But the most important force on the gas is not radiation pressure. It is the solar wind. The solar wind is a stream of charged particles, primarily protons and electrons, emitted continuously from the Sun's corona. It flows outward at speeds of several hundred kilometers per second, carrying with it the Sun's magnetic field and sweeping through the entire solar system. When the solar wind encounters a comet's coma, it interacts with the neutral gas through a process called charge exchange, A proton from the solar wind collides with a neutral molecule in the coma, say, a water molecule, and steals an electron, converting the neutral molecule into an ion and itself into a neutral atom. The newly created ion, now electrically charged, is picked up by the sun's magnetic field and carried away by the solar wind. This creates the plasma tail, also called the ion tail or gas tail. Unlike the dust tail, which is curved and yellow-white, the plasma tail is straight and blue, pointing almost exactly away from the sun regardless of the comet's direction of motion. The blue color comes from the fluorescence of ionized carbon monoxide, which emits strongly at blue wavelengths when excited by sunlight. The straightness comes from the fact that the ions are accelerated almost instantaneously to the solar wind velocity, hundreds of kilometers per second, so they stream away from the nucleus in the direction of the solar wind flow, which is nearly radial. The plasma tail can extend for millions of kilometers, far longer than the dust tail, though it is also much fainter and more diffuse. It is most easily seen in images taken through filters that isolate the emission lines of ionized molecules, or in long-exposure photographs that reveal faint structures invisible to the eye. The tail is not smooth. It often shows kinks, disconnections, and ray-like structures called streamers, caused by variations in the solar wind and interactions with the sun's magnetic field. Sometimes a portion of the tail detaches entirely, carried away by a gust of solar wind, and a new tail begins to form in its place. For 3I/Atlas, the plasma tail is still developing. The comet is producing gas at an increasing rate as it approaches the sun, and the ionization rate is rising correspondingly. The tail is faint, barely visible in ground-based images, but spectroscopic observations confirm the presence of ionized molecules, C+, H2O+, moving rapidly away from the nucleus. The tail extends perhaps a few 100,000 kilometers at present, but it will grow longer as the comet nears perihelion and the gas production peaks. At maximum activity, the plasma tail could reach tens of millions of kilometers, stretching across a significant fraction of the inner solar system. The rocket effect, the force that causes the delay in the comet's arrival, is also related to the outgassing, though it operates through a different mechanism. The rocket effect arises from the momentum carried away by escaping gas molecules. When a molecule sublimates from the surface and escapes into space, it carries momentum with it, mass times velocity. By conservation of momentum, the nucleus must experience an equal and opposite momentum change, a recoil that pushes it in the direction opposite to the escaping gas. If the outgassing is symmetric, the recoil forces cancel. But if the outgassing is asymmetric, concentrated on one side of the nucleus or oriented preferentially in one direction, the forces do not cancel, and the nucleus experiences a net thrust. The magnitude of the thrust depends on the mass loss rate and the velocity of the escaping gas. For 3I/Atlas, the mass loss rate at present is estimated at several kilograms per second, and the gas velocity is around 500 meters per second. This corresponds to a thrust of a few millinewtons, comparable to the weight of a small insect on Earth. But sustained continuously over weeks or months, it produces a measurable change in the comet's velocity. The direction of the thrust depends on where the active areas are located and how the nucleus is oriented. If the active areas are on the sun-facing side, and if the nucleus is rotating such that the outgassing occurs when the active areas are oriented in a particular direction, the thrust can either accelerate or decelerate the comet along its orbit. For 3I/Atlas, the thrust is decelerating the comet, causing it to arrive late at perihelion. This implies that the outgassing is occurring preferentially in the direction of the comet's motion, acting as a brake. The active areas are likely located such that they face forward along the orbit during peak outgassing, perhaps near the subsolar point when the comet is in a particular orientation. The exact geometry is uncertain, but the net effect is clear. The comet is slowing down, falling behind the predicted position. Arriving hours later than a purely gravitational trajectory would suggest, only took a few millinewtons to rewrite the arrival time. The interplay of forces, gravity, radiation pressure, solar wind, and the rocket effect creates a complex dynamical environment around the comet. Each force operates on different components of the coma. Gravity affects everything, holding the larger particles in orbit and curving the trajectories of the smaller ones. Radiation pressure pushes the dust away from the sun, creating the curved dust tail. The solar wind sweeps up the ionized gas, creating the straight plasma tail. And the rocket effect, subtle but persistent, alters the orbit of the nucleus itself, changing the arrival time and introducing uncertainties into the predictions. These forces do not operate in isolation. They interact, influence each other, and together they shape the comet's evolution as it falls toward the sun. A delay of several hours, measured across millions of kilometers and weeks of travel, might seem negligible, a rounding error, a minor deviation from the predicted path, but in the precise language of orbital mechanics, a few hours at perihelion represents a significant displacement, a clear signal that forces beyond gravity are at work. The delay tells a story. It speaks of ice sublimating, of gas escaping, of a nucleus that is not an inert rock but an active, evolving body responding to the sun's warmth. The delay is data, a measurement that can be converted into physical parameters, outgassing rates, thrust magnitudes, activity levels, and used to refine models of cometary behavior. The delay also reveals something more subtle: the difficulty of prediction in systems where small, hard-to-measure forces accumulate over time. The non-gravitational acceleration acting on 3I/Atlas is only a few millimeters per second squared, thousands of times weaker than the sun's gravitational pull at the same distance. For an inert body, such a small force would be irrelevant, lost in the noise of measurement uncertainty. But for a comet approaching perihelion over a period of weeks, the small force acts continuously, and its effect integrates over time. A tiny acceleration, sustained day after day, produces a measurable velocity change. The velocity change, in turn, produces a displacement, a shift in position along the orbit that grows larger the longer the force acts. This is the essence of secular perturbations: small forces that have negligible immediate effects but produce large cumulative changes over long timescales. The delay at perihelion is the cumulative result of weeks of non-gravitational acceleration, each second contributing a tiny increment to the total velocity deficit. By the time the comet reaches perihelion, the integrated effect is large enough to shift the arrival time by hours, a deviation that is easily measurable with modern observational techniques. The delay cannot be predicted in advance without knowing the outgassing rate and the orientation of the active areas, and these quantities are themselves difficult to measure or model. So the delay remains, to some extent, a surprise, an outcome that becomes known only by observing the comet's actual position and comparing it to the predicted ephemeris. Different comets produce different delays, depending on their activity levels and the specifics of their outgassing patterns. Short-period comets, which have made many close approaches to the sun and are often depleted in volatile ices, tend to produce smaller non-gravitational forces than long-period comets making their first or second perihelion passage. Some comets arrive early, accelerated by outgassing patterns that produce prograde thrust. Others arrive late, decelerated by retrograde thrust. A few comets show almost no non-gravitational effect, either because they are inactive or because their outgassing is so symmetric that the forces cancel. Each comet is unique, shaped by its individual history and composition. For 3I/Atlas, The delay provides a rare opportunity to study an interstellar comet's response to solar heating. Only a handful of interstellar objects have been detected passing through the solar system, and most of them, like 1I/Oumuamua, the first confirmed interstellar visitor, showed little or no activity, remaining dark and inert throughout their passage. 3I/Atlas is different. It is clearly active, producing a substantial coma and measurable non-gravitational forces. This suggests that its composition includes a significant fraction of volatile ices, similar to solar system comets, and that its interior has remained cold enough during its interstellar journey to preserve those ices in a relatively pristine state. The delay also provides a constraint on the comet's interior structure. The magnitude of the non-gravitational force depends on the mass loss rate, which in turn depends on the amount of surface area that is actively sublimating. If the nucleus is small and the active area is a large fraction of the total surface, the mass loss rate per unit area can be estimated and compared to laboratory measurements of ice sublimation rates at similar temperatures. This comparison suggests that 3I/Atlas is sublimating at a rate consistent with water ice at temperatures around 200 Kelvin, with perhaps 10 to 20% of the surface actively outgassing at any given time. The rest of the surface is either covered by an insulating dust mantle or consists of non-volatile material that does not sublimate. The active fraction, the percentage of the surface that is outgassing, is a key parameter in cometry science. It determines how efficiently a comet converts absorbed solar energy into gas production, and it varies widely among different comets. Some comets have active fractions approaching 50% or more, with large areas of exposed ice sublimating vigorously. Others have active fractions of only a few percent, with most of the surface covered by dust and only isolated patches or jets contributing to the coma. The active fraction can change over time as dust accumulates, as ice is depleted, or as new areas are exposed by fragmentation or erosion. For 3I/Atlas, the active fraction appears to be moderate, neither exceptionally high nor unusually low. This is consistent with a nucleus that has a mixed surface, some areas of exposed ice, some areas of dust-covered ice, some areas of non-volatile rock or organics. The rotation of the nucleus brings different areas into sunlight in turn, creating variations in the outgassing rate and the coma brightness. These variations, though difficult to measure from Earth, provide additional clues about the distribution of active areas and the shape of the nucleus. The delay in arrival time is also sensitive to the direction of the non-gravitational force, not just its magnitude. A force directed radially away from the Sun produces no change in the orbital period or perihelion time. It simply pushes the comet slightly outward, increasing the perihelion distance by a small amount, but a force directed along the orbit, either forward or backward, directly affects the orbital velocity and thus the arrival time. A backward force, opposite to the direction of motion, slows the comet and causes a delay. A forward force accelerates the comet and causes an early arrival. The fact that 3I/Atlas is arriving late indicates that the net force has a substantial component in the backward direction, suggesting that the active areas are oriented such that the outgassing preferentially opposes the orbital motion. This orientation depends on the interplay between the nucleus's rotation and the location of the active areas. If the nucleus is rotating rapidly and the active areas are near the equator, the outgassing pattern will change continuously as the nucleus spins, and the time average force may have a different direction than the instantaneous force at any given moment. If the nucleus is rotating slowly, or if the active areas are near one of the rotational poles, the outgassing pattern will be more stable, and the force direction will be more predictable. Without detailed observations of the nucleus itself, its shape, spin state, and surface features, the exact mechanism remains uncertain, but the delay is real, measurable, and significant. It is not an artifact of measurement error or orbital calculation. It is a physical phenomenon, a direct consequence of the comet's activity and the rocket effect produced by asymmetric outgassing, and it serves as a reminder that comets are not passive objects following predetermined paths. They are active participants in their own orbital evolution, capable of altering their trajectories through their response to the sun's radiation. The mathematics can describe the general behavior, can predict the average outcome, but the specifics, the exact arrival time, the precise trajectory, remain subject to the unpredictable details of sublimation, rotation, and surface geology. Only took crossing the inner solar system to prove that predictions are approximations. The delay will continue to grow, slightly, as the comet completes its approach to perihelion. The outgassing rate is increasing as the solar flux increases, and the non-gravitational force is correspondingly stronger. Each day, each hour. The comet falls a little farther behind the predicted position. The velocity deficit grows a little larger, and the arrival time shifts a little later. Observers continue to track the comet's position, refining the orbit determination, updating the models, and converging toward a final prediction for the perihelion time. But the prediction will not be perfect. It cannot be perfect. The comet does not follow the mathematics exactly. It follows the ice. The comet came from beyond. This simple statement carries profound implications. Every object in the solar system, every planet, asteroid, comet, and grain of dust, formed from the same primordial cloud of gas and dust that collapsed to create the sun roughly 4.5 billion years ago. They share a common chemistry, a common isotopic composition, a common heritage recorded in the ratios of elements and the abundance of radioactive isotopes. But 3I/Atlas did not form here. It formed elsewhere, in orbit around a different star from a different molecular cloud, in a region of the galaxy whose properties, temperature, density, composition, radiation environment, may have been different from the conditions that prevailed in the early solar nebula. The evidence for its interstellar origin lies in the orbit, a hyperbolic trajectory with eccentricity greater than one cannot result from any purely solar system process. Even the most energetic gravitational encounters with planets, close flybys of Jupiter, for instance, which can dramatically alter a comet's orbit, cannot increase the eccentricity beyond 1 unless the comet was already on a nearly escape trajectory. And objects born in the solar system, even those in the distant Oort cloud, are gravitationally bound to the sun. They may have orbital periods of millions of years, and they may travel thousands of astronomical units from the sun, but their orbits remain elliptical, closed, returning eventually to the inner solar system. A hyperbolic orbit, by contrast, is open. It arrives from infinity, swings past the sun once, and departs to infinity, never to return. The velocity at infinity, the speed the comet had relative to the sun before the sun's gravity began to accelerate it, can be calculated from the orbital elements. For 3I/Atlas, this velocity is approximately 26 kilometers per second, which is typical for stars in the solar neighborhood. The sun orbits the galactic center at roughly 220 kilometers per second, and nearby stars have similar orbital velocities but slightly different directions, resulting in relative velocities of a few tens of kilometers per second. This suggests that 3I/Atlas was ejected from a planetary system belonging to a star that is, or was, relatively close to the sun, within a few parsecs. Perhaps, though the exact distance and direction cannot be determined from the trajectory alone, the ejection mechanism is uncertain. One possibility is gravitational scattering by a giant planet, the same process that populates the Oort cloud in the solar system. In the early stages of planetary system formation, when the protoplanetary disk is still filled with planetesimals and the giant planets are migrating inward or outward under the influence of gravitational interactions. Countless small bodies are flung onto highly eccentric orbits. Some fall into the star. Some are ejected entirely, sent on hyperbolic trajectories that carry them out of the planetary system and into interstellar space. It is estimated that for every object that remains in a planetary system's Oort cloud, dozens or hundreds are ejected. These ejected bodies become free-floating, wandering through the galaxy until they chance to pass close to another star and are perturbed onto a new trajectory. Another possibility is a close stellar encounter. Stars in young clusters are densely packed, and close approaches, within a few hundred astronomical units, are not uncommon. Such an encounter can destabilize the outer regions of a planetary system's Oort cloud, sending showers of comets either into the inner system or out into interstellar space. The Sun likely experienced several such encounters during its first few 100 million years, when it was still part of the stellar nursery where it formed, before it drifted away into the relative isolation of the galactic disk. Other stars underwent similar histories, and some fraction of their Oort cloud populations were lost to interstellar space. Once ejected, the comet travels through the galaxy as an independent object, no longer bound to any star. Its trajectory is determined by the gravitational field of the galaxy as a whole, the combined pull of billions of stars, the dark matter halo, the spiral arms with their enhanced stellar densities. The galactic gravitational field is smooth on the scale of a comet's orbit, so the trajectory is nearly a straight line, or rather, a gentle curve following a galactic orbit not so different from that of a star. The comet moves at tens of kilometers per second, covering parsecs in millions of years, light years in tens of millions of years. It is cold, receiving only the faint starlight of the Milky Way, which provides negligible heating. The surface temperature equilibrates at perhaps 10 or 20 Kelvin, just a few degrees above the cosmic microwave background. At these temperatures, even the most volatile ices, carbon monoxide, methane, nitrogen, remain solid. There is no sublimation, no outgassing, no activity. The comet is inert, frozen. A dark grain drifting through the interstellar medium, it may occasionally pass through molecular clouds, regions of slightly higher density where the ambient gas pressure and radiation environment differ slightly from the near vacuum of open space. But these encounters have little effect. The comet is too small to accrete material, too cold to be altered by radiation, too dense to be disrupted by the weak tidal forces of the galaxy. It simply drifts, unchanging, for millions or tens of millions of years, until it happens to pass close to another star. The encounter with the solar system is, in a sense, random. The comet's trajectory through the galaxy is determined by its ejection velocity and the galactic gravitational field, both of which are effectively unpredictable on the timescales relevant to individual objects. The comet could have passed through any of billions of stellar systems, or through none, continuing its journey through the galaxy indefinitely. But it passed close enough to the Sun, within a few light years, perhaps, that the Sun's gravity began to influence its trajectory, bending it inward, pulling it toward the inner solar system. The encounter is brief, lasting only a few years from the comet's perspective, but it is enough to wake the ice, to bring warmth and light and activity after an eternity of cold and darkness. The chemistry of the comet may differ from that of solar system comets, reflecting the different conditions in its birth environment. The ratio of deuterium to hydrogen in the water ice, for instance, depends on the temperature and density of the molecular cloud from which the planetary system formed. The abundance of carbon monoxide relative to water depends on the carbon-to-oxygen ratio and the thermal history of the ice. The isotopic ratios of nitrogen, oxygen, and carbon provide fingerprints of the nucleosynthetic processes that created the elements and the subsequent chemical processing in the protoplanetary disk and molecular cloud. Measuring these ratios in an interstellar comet offers a unique opportunity to compare the chemistry of different stellar systems and to test models of planet formation and molecular cloud evolution. But the measurements are difficult. The comet is faint, and the spectroscopic observations required to determine isotopic ratios and molecular abundances demand large telescopes, long integration times, and sensitive detectors. Some measurements have been attempted. Spectroscopic observations of the coma have detected water vapor, carbon monoxide, and other common cometary volatiles, but the signal-to-noise is low, and the derived abundances carry large uncertainties. The deuterium-to-hydrogen ratio, for instance, cannot be reliably determined from ground-based observations and would require space-based ultraviolet spectroscopy or a close flyby by a spacecraft equipped with a mass spectrometer. So the question of whether 3I/Atlas is chemically distinct from solar system comets remains open. Preliminary results suggest that it is similar, water-rich, with carbon monoxide and carbon dioxide as major secondary components, and with trace amounts of organic molecules and cyanogen, but similar does not mean identical. Subtle differences in isotopic ratios or molecular abundances might exist, hidden in the noise of the current observations, waiting for better data to reveal them. Or the comet might be indistinguishable from solar system comets, suggesting that the chemistry of planet formation is universal, at least for sun-like stars in similar galactic environments. Only took crossing a few light years to find out it's made of ice. Just like the others. The interstellar origin also raises questions about the comet's age. Solar system comets are as old as the solar system itself, 4.5 billion years, give or take a few million. But 3I/Atlas could be older or younger. Depending on when its parent star formed, stars form continuously in the galaxy, with some stellar nurseries producing stars billions of years ago and others forming stars at the present day. If 3I/Atlas was ejected from a young planetary system, one formed only a few 100 million years ago, it might be significantly younger than solar system comets, perhaps containing pristine ices that have undergone less radiation processing and cosmic ray exposure. If it was ejected from an old planetary system, one formed 8 or 10 billion years ago, before the Sun existed, it might be ancient, carrying isotopic signatures of nucleosynthesis in stars that have long since died. There is no direct way to determine the comet's age from Earth-based observations. Age dating requires laboratory analysis of samples, measurements of radioactive isotopes and their decay products, techniques that cannot be applied to a remote object observed only through telescopes, so the age remains unknown, a mystery embedded in the frozen nucleus. The comet is old in the sense that it has been traveling through interstellar space for a long time, millions of years at least, perhaps tens of millions. But how old it is in absolute terms, how long ago it first condensed from the disk of gas and dust around its parent star, is unknowable without a sample return mission or at least a close flyby with sophisticated instruments. The comet does not remember where it came from. It carries no record of its ejection, no map of its trajectory through the galaxy, no marker identifying its parent star. It is simply here, falling toward the Sun, responding to warmth and light as any comet would. Its interstellar origin is recorded only in its orbit, in the hyperbolic trajectory that will carry it back out into the galaxy after perihelion, and in the chemical and isotopic signatures that might, if they could be measured precisely enough, distinguish it from the native population of solar system comets. But those signatures are faint, ambiguous, buried in the noise of limited observations. What is certain is that the comet has traveled farther than any solar system comet ever will. It has crossed the space between stars, survived the cold and radiation of the interstellar medium, and arrived here by chance, offering a brief glimpse of the ice and dust that exist in planetary systems beyond our own. In a few months, it will leave, climbing back out of the Sun's gravity well and resuming its journey through the galaxy, carrying with it the scars of this encounter: mass lost to sublimation, surface altered by solar heating, orbit changed by the sun's gravitational influence, but otherwise unchanged. Still the same frozen remnant of another star's planetary debris. Perihelion is not a place, but a moment. The instant when the comet's distance from the sun reaches its minimum value for 3I/Atlas. This moment occurs at a distance of approximately 0.6 astronomical units, 90 million kilometers, closer than the orbit of Venus, well within the region where solar radiation is intense and surface temperatures climb high enough to drive vigorous sublimation. The approach to perihelion is gradual, the distance shrinking day by day, the solar flux increasing in proportion to the inverse square of the distance, at 1 astronomical unit. The distance of Earth. The solar constant is about 1,360 watts per square meter at 0.6 AU. It is roughly 3,800 watts per square meter, nearly 3 times as intense. The nucleus responds to this increasing flux with increasing activity. The surface temperature, which was perhaps 150 Kelvin when the comet crossed Earth's orbit, climbs to 200 Kelvin, then 250, then approaches or exceeds the melting point of water ice, 273 Kelvin, though liquid water does not form in the vacuum of space. Instead, the sublimation rate accelerates. Water ice, which sublimates slowly at low temperatures, now transforms to vapor at rates that can approach kilograms per second per square meter of exposed ice. The total mass loss rate, integrated over all active areas, may reach tens or even hundreds of kilograms per second, a prodigious outpouring of gas and dust that feeds the expanding coma and tails. The brightness of the coma increases correspondingly. Comets are often brightest at or shortly after perihelion, when the outgassing rate peaks and the coma is most dense and extensive. For 3I/Atlas, the predicted peak brightness is approximately magnitude 6 or 7, just at the edge of naked eye visibility under dark skies. Though well within reach of binoculars or small telescopes, the brightening is not uniform. It varies with the rotation of the nucleus, with the changing distance to the sun, and with any outbursts or fragmentation events that might occur. Observers monitor the brightness daily, plotting light curves that track the comet's evolution and searching for deviations from the expected smooth increase. The surface of the nucleus, now subjected to intense solar radiation, undergoes thermal stress. The temperature difference between sunlit and shadowed regions can exceed 100 Kelvin, creating gradients that induce mechanical strain in the ice. Ice, though often thought of as brittle and rigid, can deform under stress, particularly at temperatures near the melting point where the material is more ductile. Fractures propagate. Existing cracks widen. Blocks of ice and rock, weakly bonded to the surface, may break free and tumble away, carried off by the escaping gas or dislodged by the thermal expansion and contraction of the surface. Sublimation also creates erosion. As ice transforms to vapor, it leaves behind any non-volatile material, dust, rock, organic compounds, that was mixed into the ice. This material accumulates on the surface, forming a lag deposit or mantle that insulates the underlying ice and reduces the sublimation rate. But the mantle is not stable. It can be disrupted by the pressure of gas escaping from below, by impacts from small meteoroids, or by the mechanical forces associated with rotation and thermal stress. When the mantle is breached, fresh ice is exposed and sublimation resumes, sometimes explosively. These events, called outbursts, can produce sudden increases in brightness and gas production, lasting hours or days before declining as the exposed ice is exhausted or covered again by dust. 3I/Atlas has not yet exhibited any major outbursts, at least none that have been detected from Earth. The brightening has been steady, predictable, consistent with models that assume gradual warming and increasing sublimation as the comet approaches perihelion. But the potential for an outburst remains, particularly at perihelion when the thermal stress is greatest and the surface is most dynamic. A single outburst, if large enough, could temporarily increase the comet's brightness by a magnitude or more and release a plume of gas and dust that would alter the appearance of the coma and possibly the orbit itself. The rotation of the nucleus also affects the thermal environment. If the rotation period is short, a few hours, the surface does not have time to reach thermal equilibrium with the incident sunlight. Instead, the temperature oscillates rapidly, rising when a given area rotates into sunlight and falling when it rotates into shadow. This creates a diurnal temperature variation that can be tens of Kelvin, superimposed on the slower seasonal variation caused by the changing distance to the sun. If the rotation period is long, days or longer, the surface can reach higher peak temperatures because there is more time to absorb energy before rotating into shadow. But the average temperature may be lower because the night side has more time to cool. For 3I/Atlas, the rotation period is estimated at several hours, though the exact value remains uncertain. This suggests that the surface experiences rapid day-night cycles, with temperatures rising and falling on timescales comparable to the rotation period. The subsurface, insulated by the low thermal conductivity of porous ice and dust, remains cooler and more stable, with temperatures that change more slowly and lag behind the surface temperature by hours or days. This creates a thermal wave that propagates inward, driving sublimation not just at the surface, but also from subsurface layers where ice is warmed to the sublimation temperature by the slowly diffusing heat. The gas produced by sublimation does not escape immediately. It must first diffuse through the porous mantle, if one exists, or through the tortuous network of voids and fractures that permeate the nucleus. This diffusion process slows the escape of gas and creates a delay between the absorption of solar energy and the peak outgassing rate. The delay, called the thermal lag, can be several hours or longer, depending on the thickness and porosity of the overlying material. The result is that peak outgassing occurs not at local noon, when the solar flux is maximum, but several hours later, when the subsurface ice has had time to warm. This lag is one of the factors that contributes to the asymmetric outgassing and the resulting non-gravitational forces. Perihelion is also the moment of maximum gravitational stress. The sun's tidal force, the difference in gravitational pull between the near and far sides of the nucleus, is inversely proportional to the cube of the distance. At perihelion, the tidal force is stronger than at any other point in the orbit, though still far too weak to disrupt a solid, coherent body. But if the nucleus is a loose aggregate, held together only by weak cohesive forces and the negligible self-gravity, the tidal stress could be enough to pull it apart. This is thought to be the mechanism behind the tidal disruption of some comets that pass very close to the sun, within a few solar radii waves, where the tidal force exceeds the material strength by a large margin. For 3I/Atlas, at a perihelion distance of 0.6 AU, the tidal force is far too weak to cause disruption. The material strength of even the weakest ice is many orders of magnitude greater than the tidal stress at this distance. But other factors, the thermal stress, rotation, outgassing pressure, may combine with the tidal force to weaken the nucleus and promote fragmentation. The nucleus is already under strain from the thermal gradients and the mechanical forces associated with outgassing. If a fracture propagates at just the wrong moment, if a weakened region gives way under the combined stress, the nucleus could split, sending fragments on slightly different trajectories and creating multiple comae within the larger cloud. Only took 4.5 billion years to find out if it survives the furnace. Perihelion passage lasts only hours. The comet's velocity at perihelion is at its maximum, several tens of kilometers per second, so it sweeps through the innermost part of its orbit quickly, spending only a brief interval at the closest distance before the distance begins to increase again. The moment of perihelion itself is anticlimactic. There is no dramatic event, no sudden change in appearance or behavior. The comet simply reaches the minimum distance. The velocity vector rotates from inward to outward, and the recession begins. The solar flux begins to decrease. The surface temperature begins to fall. The sublimation rate begins to decline. The comet, having survived its closest approach, begins the long climb back out of the inner solar system. But the effects of perihelion linger. The nucleus has lost mass, perhaps millions of kilograms, possibly more, carved away by sublimation and carried off as gas and dust. The surface has been altered, eroded, fractured, perhaps stripped of its dust mantle in some areas and buried under fresh deposits in others. The orbit has been changed by the cumulative effect of non-gravitational forces. The arrival time shifted by hours. The trajectory bent slightly from the path that gravity alone would have prescribed, and the coma, now at its maximum extent and brightness, continues to expand, carrying the evidence of perihelion outward into space, a growing cloud of molecules and particles that will persist for weeks or months before dispersing into the solar wind. The tail that points away from the sun is not one tail, but two, sometimes three, each composed of different materials and shaped by different forces. The most visually striking is the dust tail, broad and curved, glowing yellow-white in reflected sunlight. It is formed by particles ranging from submicron grains to millimeter-sized pebbles, all expelled from the nucleus by the drag of escaping gas and subsequently pushed outward by solar radiation pressure. The curvature of the dust tail reflects the fact that particles are not accelerated instantaneously, but rather pushed gradually over days or weeks, during which time the comet itself continues to move along its orbit. The result is a curved arc that sweeps backward from the nucleus, broader and more diffuse at greater distances, where particles released at different times have dispersed along their individual trajectories. The plasma tail, by contrast, is narrow and straight, pointing almost exactly in the anti-sunward direction regardless of the comet's motion. It is composed of ionized gas, molecules that have lost one or more electrons through photoionization or interaction with the solar wind. The ions, electrically charged, are swept up by the sun's magnetic field, which is carried outward by the solar wind at speeds of several hundred kilometers per second. This interaction accelerates the ions to high velocities almost immediately, so they stream away from the nucleus along the magnetic field lines, forming a tail that can extend for millions or tens of millions of kilometers. The plasma tail glows with its own light, fluorescing at specific wavelengths characteristic of the ionized molecules: blue for carbon monoxide ions, red for ionized water, green for cyanogen. A third component, sometimes visible in comets with high dust production rates, is the antitail, a faint, spike-like extension that appears to point toward the sun, in the opposite direction from the dust and plasma tails. The antitail is not actually pointing sunward. It is an optical illusion caused by viewing the dust tail edge on. The dust particles, spread along the comet's orbital plane, form a thin sheet that extends both forward and backward from the nucleus. When the Earth passes through or near the plane of this sheet, the particles ahead of the nucleus along the orbit appear projected against the sky in a direction that seems sunward, creating the illusion of a tail pointing the wrong way. The anti-tail is typically visible only for a few days or weeks, during the time when the viewing geometry is favorable. For 3I/Atlas, the dust tail is now prominent, extending perhaps 2 or 3 degrees across the sky as seen from Earth, several million kilometers in actual length. The tail is broad at the base, near the coma, where particles of all sizes contribute to the brightness, and narrower toward the tip, where only the smallest, fastest moving particles are found. The color is slightly yellowish, matching the color of sunlight reflected from the dust grains, though the exact hue depends on the composition and size distribution of the particles. Silicate grains, rich in magnesium and iron, produce a slightly reddish tint. Carbonaceous grains, rich in organic compounds, produce a more neutral or grayish color. The dust tail is dynamic, changing from night to night as new particles are added and old particles drift farther from the nucleus. Photographs taken days apart show the tail lengthening, broadening, and sometimes developing subtle streamers or fans, features caused by variations in the dust production rate or the direction of the dust ejection. These features are not fixed but evolve and disperse as the particles spread along their trajectories. Sometimes a bright ray or jet appears in the tail, marking a period of enhanced dust production from a specific active area on the nucleus. The ray persists for a few days before fading as the particles disperse and the rotation of the nucleus carries the active area into shadow. The plasma tail is fainter but more structured. It shows kinks and waves caused by variations in the solar wind and the interaction between the sun's magnetic field and the ionized gas. The solar wind is not steady. It varies in speed, density, and magnetic field strength, responding to activity on the sun's surface, flares, coronal mass ejections, the rotation of magnetically active regions. When a gust of fast solar wind overtakes the slower wind ahead of it, a compression region forms, creating a shock wave that sweeps through the interplanetary medium. When this shock encounters the comet's plasma tail, it compresses the ionized gas, brightens the tail temporarily, and sometimes causes a disconnection event, a dramatic severing of the tail that sends a detached portion streaming away into space while a new tail begins to form near the nucleus. Disconnection events are spectacular when they occur, creating the appearance of a comet shedding its tail and growing a new one within hours. The detached portion drifts away, carried by the solar wind, gradually fading as the ions recombine with electrons and become neutral again. The new tail grows rapidly, fed by fresh gas from the nucleus, and within a day or two, the plasma tail is restored, often indistinguishable from its pre-disconnection appearance except in the fine details of its structure. For 3I/Atlas, no major disconnection events have been observed yet, but the plasma tail shows subtle variations in brightness and width, hinting at the turbulent environment in which it exists. The formation of the plasma tail begins with the ionization of neutral gas in the coma. Ultraviolet photons from the sun strike molecules like water, carbon monoxide, and carbon dioxide, knocking off electrons and creating ions. The ionization rate depends on the intensity of the ultraviolet flux and the density of the neutral gas, both of which peak near the nucleus and decline with distance. The ions, once created, are picked up by the solar wind's magnetic field through a process that involves the freezing in of magnetic field lines to the ionized plasma. The sun's magnetic field, carried outward by the solar wind, cannot penetrate into regions of high electrical conductivity without dragging the charged particles along with it. So the ions are accelerated, pulled along by the magnetic field, and swept away from the nucleus. The acceleration is rapid. Within a few tens of thousands of kilometers from the nucleus, the ions reach velocities comparable to the solar wind speed, 300 to 500 kilometers per second. At these velocities, the ions escape the coma entirely within hours, forming the extended plasma tail. The tail is replenished continuously by new ions created near the nucleus, so it persists as long as the comet is actively outgassing. The length of the plasma tail is limited not by the supply of ions, but by the rate at which ions recombine with electrons and become neutral, and by the dispersion of the tail as the ions spread out along the magnetic field lines. The dust tail, in contrast, evolves more slowly. Dust particles, once released from the nucleus, are not accelerated instantaneously but pushed gradually by radiation pressure. The acceleration depends on the particle size. Smaller particles are pushed harder and continues as long as the particles are illuminated by sunlight. Over days or weeks, the particles drift away from the nucleus, spreading out along curved trajectories that reflect the balance between radiation pressure and the sun's gravity. The smallest particles, with beta values greater than 1, escape the solar system entirely, moving on hyperbolic paths that will eventually carry them into interstellar space. Larger particles, with beta values less than 1, remain bound to the sun and enter elliptical orbits that may intersect the orbits of planets. These particles, dispersed along the comet's orbit, form meteoroid streams, trails of debris that persist for centuries or millennia after the comet itself has moved on. When Earth's orbit intersects one of these streams, the particles enter the atmosphere at high velocity and burn up, creating meteors, shooting stars visible in the night sky. Many of the annual meteor showers, like the Perseids or the Leonids, are caused by Earth passing through the debris trails of known comets. For 3 I/Atlas, the orbit does not intersect Earth's orbit, so the comet will not produce a meteor shower visible from Earth, but the particles it sheds will remain in the solar system, gradually spreading out and mixing with the background population of interplanetary dust. The tails, both dust and plasma, are ephemeral. They exist only while the comet is active, only while the nucleus is sublimating and producing gas and dust. As the comet recedes from the sun, the sublimation rate declines, the gas production drops, and the tails begin to fade. The plasma tail disappears first, within days or weeks of perihelion, as the ionization rate falls below the recombination rate and the supply of new ions is exhausted. The dust tail lingers longer, sustained by particles already in flight, but it too gradually disperses, the particles spreading out and becoming too faint to detect. Within a few months of perihelion, the comet's tails are gone, and only the coma remains, a fading halo around the invisible nucleus, shrinking as the comet climbs back out toward the orbit of Mars and beyond. Only took a few million kilometers of ice to paint a tail across the sky. The tails are the comet's signature, the visible manifestation of processes occurring on a body too small and dark to see. They are both beautiful and transient, existing only for the brief interval when the comet is close enough to the sun to sublimate vigorously. They point away from the sun, always. Regardless of the comet's direction of motion, a visual reminder that the force shaping them is not the comet's velocity, but the outward pressure of sunlight and the solar wind. And they carry away, particle by particle, molecule by molecule, the substance of the nucleus, dispersing it into space where it will drift for eons, perhaps to be incorporated into new worlds, new comets, new cycles of formation and destruction. Observatories around the world track the comet's progress, each contributing pieces to the larger puzzle of understanding its behavior. Ground-based telescopes, ranging from small amateur instruments to large professional observatories, image the comet nightly, measuring its position against the background stars and monitoring its brightness. The positions are reported to the Minor Planet Center, the international clearinghouse for observations of asteroids and comets, where they are collected, processed, and used to refine the orbital determination. Each observation adds to the data set, reducing the uncertainties in the orbit and allowing more accurate predictions of the comet's future position. But the observations are not perfect. Atmospheric turbulence blurs the images, making it difficult to pinpoint the exact center of the coma where the nucleus is located. The coma itself is diffuse and asymmetric, sometimes showing jets or fans that offset the brightness peak from the true position of the nucleus. Clouds, moonlight, and light pollution interfere with observations, limiting the number of clear nights and reducing the signal-to-noise ratio in the images. And the comet is faint, especially when far from the Sun, requiring long exposures and sensitive detectors to capture enough light for accurate measurements. Spacecraft offer better viewing conditions, no atmosphere, no weather, continuous observing time, but spacecraft missions to comets are rare and expensive, requiring years of planning and development. No mission was planned for 3I/Atlas. Its interstellar origin was discovered only after it entered the inner solar system. Too late to design, build, and launch a spacecraft that could intercept it before perihelion. So the observations remain ground-based, supplemented by space telescopes like Hubble and James Webb, which can provide higher-resolution images and spectroscopic data free from atmospheric absorption. The orbital refinement is an iterative process. Each new batch of observations is added to the dataset, and the orbit is recalculated using least squares fitting or similar techniques that minimize the difference between observed and predicted positions. The orbit determination software accounts for gravitational perturbations from the planets, relativistic corrections, and, increasingly, non-gravitational forces. The non-gravitational forces are parameterized using simple models, often just two parameters, one for the radial component of the force and one for the transverse component, that are adjusted to fit the observations. The models are not physically detailed. They do not attempt to simulate the outgassing on a grain-by-grain basis or to model the thermal properties of the nucleus. They are empirical, designed to capture the average effect of non-gravitational forces on the orbit without requiring detailed knowledge of the comet's interior. As more observations accumulate, the model parameters converge. The radial component of the non-gravitational force is found to be small, consistent with outgassing that is roughly symmetric in the radial direction. The transverse component, which affects the orbital velocity, is larger and negative, indicating that the comet is being decelerated along its orbit. This confirms the earlier inference that the comet is arriving late at perihelion. The magnitude of the transverse force, combined with estimates of the nucleus size and mass, allows a rough calculation of the mass loss rate and the active fraction of the surface. The results are consistent with a moderately active comet, sublimating water ice at temperatures typical of cometary nuclei at this distance from the Sun. The active fraction is estimated at 10 to 20%, meaning that most of the surface is either covered by dust or composed of non-volatile material. The total mass loss between the time the comet became active and perihelion is estimated at several million kilograms, perhaps as much as 10 million, a small but measurable fraction of the nucleus's total mass, which is estimated at around 10 billion kilograms for a 3-kilometer body with a density of half that of water ice. The brightness measurements provide an independent check on the activity level. The comet's brightness, as measured in visible light, is dominated by the dust in the coma. The total amount of light reflected by the dust depends on the dust production rate, the particle size distribution, and the albedo of the dust grains. By modeling the brightness as a function of time and distance from the Sun, astronomers can estimate the dust production rate and compare it to the gas production rate inferred from spectroscopic observations. The ratio of dust to gas production, called the dust-to-gas ratio, varies among comets and provides clues about the composition and structure of the nucleus. For 3I/Atlas, the dust-to-gas ratio appears to be close to 1, meaning that the comet is producing roughly equal masses of dust and gas. This is typical of many comets, though some are dustier, producing more dust than gas, and others are more gas-rich. The dust-to-gas ratio can change over time as the surface evolves, as dust accumulates in some areas and is blown away in others, or as fragmentation exposes fresh ice that produces gas-rich outflows. Monitoring the dust-to-gas ratio as the comet approaches and recedes from perihelion provides information about how the surface is changing in response to solar heating. Spectroscopic observations reveal the chemical composition of the gas in the coma. Different molecules emit or absorb light at specific wavelengths, creating spectral lines that can be identified and measured. Water vapor, the dominant component of most comets, produces lines in the ultraviolet and infrared. Carbon monoxide produces lines in the ultraviolet and submillimeter. Cyanogen produces a characteristic green emission in the visible. By measuring the intensities of these lines and comparing them to models of fluorescence and molecular emission, astronomers can determine the production rates of individual species and the relative abundances of different molecules. The spectroscopic data for 3Y/Atlas show water vapor as the dominant outgassing species, as expected, with carbon monoxide and carbon dioxide as secondary components. Trace amounts of cyanogen, methane, and ammonia have also been detected, though the measurements are near the detection limit and carry large uncertainties. The relative abundances are broadly similar to those of solar system comets, suggesting that the chemistry of ice formation is not dramatically different in the comet's parent system. But subtle differences may exist. The ratio of carbon monoxide to water, for instance, might be slightly higher or lower than typical solar system values. And these differences, if they are real and not just measurement noise, could provide clues about the temperature and chemistry of the protoplanetary disk where the comet formed. Isotopic ratios are particularly valuable for comparing comets from different origins, but they are also particularly difficult to measure. The spectral lines of isotopologues, molecules that differ only in the isotopes of their constituent atoms, are often closely spaced and require high spectral resolution to separate. The deuterium to hydrogen ratio in water, for instance, requires measuring the intensities of lines from HDO and H2O, which are in different wavelength regions and require different observing techniques. For 3I/Atlas, attempts have been made to measure this ratio, but the comet is too faint and the signal too weak to obtain a reliable result. The best that can be said is that the ratio is not dramatically different from solar system comets, not 10 times higher or lower, but whether it is precisely the same or slightly different remains unknown. The rotation period, inferred from variations in the coma brightness and spectroscopic measurements, is estimated at approximately 8 hours, though the uncertainty is several hours. This is consistent with the rotation periods of other cometary nuclei of similar size, which typically range from a few hours to a few days. A rotation period of 8 hours corresponds to a rotational velocity at the equator of roughly half a meter per second for a 3-kilometer nucleus, fast enough to produce measurable centrifugal forces, but not fast enough to threaten disruption. The rotation may not be a simple spin, but rather a complex tumbling motion, with the nucleus rotating about a changing axis. Such tumbling is common among small, irregular bodies and can complicate the interpretation of brightness variations and outgassing patterns. The observations continue, day after day, building a detailed record of the comet's evolution as it approaches perihelion. Each night's data adds to the understanding of the orbit, the activity, the composition, and the structure. Each measurement refines the parameters, reduces the uncertainties, and sometimes reveals surprises, an unexpected outburst, a sudden brightening, a change in the spectral signature that hints at the exposure of fresh ice or a different volatile compound. The comet does not cooperate. It does not follow the models exactly. It deviates, varies, surprises, and the observers respond, recalculating, remodeling, refining their understanding in an ongoing dialogue between prediction and observation. Only took decades of building telescopes to watch a visitor pass through. The recalculated perihelion time, updated daily as new observations are incorporated, converges toward a final value that is several hours later than the original prediction based on purely gravitational models. The delay is real, measurable, and significant. It represents the cumulative effect of weeks of non-gravitational acceleration, the integrated thrust of escaping gas pushing the comet backward along its orbit, the final perihelion time, predicted with an uncertainty of perhaps a few minutes, becomes a target for observers around the world. A specific moment when the comet will be at its closest to the Sun, its brightest, its most active. But even this final prediction is not perfect. The non-gravitational forces continue to vary as the comet approaches perihelion. As the outgassing rate increases and the rotation brings different active areas into sunlight, the uncertainty in the perihelion time reflects not just measurement errors, but the fundamental unpredictability of cometary activity. The models can describe the average behavior, the general trend, but they cannot predict the exact moment to the second. That level of precision is beyond reach. Lost in the chaos of sublimating ice and rotating nuclei and the stochastic variations in solar wind and surface fractures, the comet does not care about the predictions. It simply continues its fall, sublimating, rotating, shedding mass, and approaching the moment when the distance to the Sun will reach its minimum and the long climb outward will begin. The nucleus does not fragment as a single catastrophic event, but rather as a gradual process. A slow coming apart that may have begun weeks or even months before it becomes visible in telescopic observations. The fragmentation of cometary nuclei is common, particularly among comets making close approaches to the Sun or experiencing their first perihelion passage in the inner solar system. The mechanisms are varied and not fully understood, but they involve thermal stress, mechanical weakness, outgassing pressure, rotational forces, and the pre-existing fractures that may date back to the comet's formation or to collisions during its long journey through space. Thermal stress is one of the primary drivers, as the surface heats and cools with the rotation of the nucleus and the changing distance to the Sun. Temperature gradients develop within the ice. The outer layers warm and expand while the interior remains cold and contracted. This differential expansion creates strain, particularly at boundaries between materials with different thermal properties: ice and rock, porous dust and solid ice, volatile rich regions and volatile depleted regions. If the strain exceeds the tensile strength of the material, fractures form. Existing fractures widen. Blocks of ice become detached from the main body, held in place only by weak cohesive forces or the confining pressure of overlying material. Outgassing provides the force to dislodge these weakly attached blocks, as ice sublimates beneath a dust mantle or within the interior of the nucleus. Gas pressure builds up in pockets and voids. The pressure is not high by terrestrial standards, perhaps only a few pascals or tens of pascals, but it acts over large areas and against material that has negligible tensile strength. When a fracture reaches the surface, the gas escapes explosively, carrying with it dust and chunks of ice. If the fracture is deep and the gas pressure high enough, the escaping gas can lift entire blocks of material, sending them on ballistic trajectories away from the nucleus. Rotation contributes centrifugal forces that, for a rapidly spinning nucleus, can approach or exceed the material strength. The centrifugal acceleration at the equator of a 3-kilometer nucleus rotating with an 8-hour period is only a fraction of a millimeter per second squared, far less than the surface gravity of Earth, but comparable to the self-gravity of the nucleus, which is also only a fraction of a millimeter per second squared. If the rotation is rapid enough, or if the nucleus is elongated and spinning about its short axis, the centrifugal forces can overcome the weak cohesive forces holding the nucleus together, and material at the equator can be flung off into space. For 3I/Atlas, the first sign of fragmentation appears as a subtle elongation of the coma, a slight asymmetry in the brightness distribution that suggests the presence of multiple condensations, bright regions within the coma that mark the positions of individual fragments. high-resolution images, taken with large telescopes under excellent seeing conditions, reveal 2 or possibly 3 distinct peaks in the brightness profile, separated by a few thousand kilometers. The peaks are not sharp. They are diffuse, each surrounded by its own small coma of gas and dust, and they overlap significantly, making it difficult to determine how many fragments are present or how large they are. The fragments are moving apart slowly, drifting away from each other at speeds of only a few meters per second. This is consistent with a gentle separation, caused perhaps by differential outgassing, one fragment producing more gas than the other and experiencing a slightly different rocket effect, or by the slow dispersal of material that was weakly bound and simply drifted apart when the cohesive forces failed. The fragments remain close enough that their comae merge, creating the appearance of a single elongated coma when viewed at lower resolution. But, over days and weeks, the separation increases, and the individual fragments become more distinct. It is not certain whether the fragmentation occurred recently, within days or weeks of the observation, or whether it occurred earlier and is only now becoming visible as the fragments drift farther apart. Cometary nuclei can split months before perihelion and remain close enough that the fragments are not resolved until they have separated by tens of thousands of kilometers. The timing of the fragmentation affects the interpretation. If the split occurred recently, it suggests that the thermal stress or outgassing pressure has only recently exceeded the material strength. If it occurred earlier, it suggests that the nucleus was already fractured and the fragments have been slowly drifting apart throughout the approach to perihelion. Observers monitor the fragments closely, imaging them nightly and measuring their positions and brightnesses. The fragments are designated with letters: Fragment A, Fragment B, and possibly Fragment C, though the designations are tentative because the third condensation is faint and may be a transient feature rather than a true fragment. Fragment A is the brightest, accounting for perhaps 60 or 70% of the total light. Fragment B is fainter, accounting for most of the remaining light. If Fragment C exists, it is very faint, contributing only a few percent to the total brightness. The relative brightnesses provide clues about the sizes of the fragments. If the fragments have similar compositions and albedos, the brightness ratio should reflect the ratio of surface areas, which in turn reflects the ratio of sizes. Fragment A, being roughly twice as bright as Fragment B, is likely somewhat larger, perhaps 1.5 times the diameter. If the relationship between brightness and size is linear, this suggests that the original nucleus has split into one large piece and one or more smaller pieces, rather than fragmenting into many pieces of comparable size. The separation velocity, estimated from the rate at which the fragments are drifting apart, is a few meters per second. This is much slower than the escape velocity would be if the fragments were ejected explosively, suggesting that the separation was gentle, driven by small differences in outgassing or rotation rather than by a violent disruption. The low separation velocity also implies that the fragments could potentially recollide if their trajectories happen to cross again. Though this is unlikely given the complexity of the orbital dynamics and the additional perturbations from outgassing, fragmentation complicates the orbit determination. Each fragment experiences its own non-gravitational forces, depending on its size, shape, rotation, and activity level. The fragments follow slightly different trajectories, arriving at perihelion at slightly different times and at slightly different distances from the Sun. Observers must now track multiple objects instead of one, and the orbit determination becomes more complex, requiring separate solutions for each fragment. The predictions for perihelion passage, already uncertain due to non-gravitational forces, become even more uncertain as the fragments evolve independently. The fragmentation also raises questions about the ultimate fate of the fragments. Will they survive perihelion, or will they disintegrate entirely, crumbling into smaller and smaller pieces, until nothing remains but a dispersing cloud of dust. Some fragments of other comets have survived for months or years after splitting, gradually fading as they exhaust their volatile ices. Others have disintegrated within days or weeks, breaking apart repeatedly until they are too small and faint to detect. The outcome depends on the size and composition of the fragments, the intensity of the solar heating, and the mechanical strength of the material. For 3I/Atlas, the fragments are still visible and still active as they approach perihelion. They have not disintegrated yet, but the risk remains, particularly at perihelion when the thermal stress peaks and the outgassing is most vigorous. Each fragment is now a small comet in its own right, with its own coma, its own outgassing pattern, its own response to solar heating. And each fragment is fragile, held together by forces barely stronger than the stresses trying to pull it apart. Only took a few million years in the cold to finally break apart in the warmth. The fragmentation is visible evidence of the comet's transient nature, a reminder that these bodies are not solid and permanent, but fragile and ephemeral. They survive for billions of years in the cold of the outer solar system or interstellar space, but when they fall into the inner solar system and experience the sun's heat, they begin to disintegrate. The process is slow, weeks or months for a close perihelion passage, years or decades for a more distant one, but it is inexorable. The comet sheds mass with every orbit, loses volatiles with every perihelion, and eventually exhausts its supply of ice, leaving behind only a dark, inert remnant that is indistinguishable from an asteroid. For 3I/Atlas, this is the only perihelion passage it will ever experience. The hyperbolic orbit ensures that the comet will not return. It will pass through the inner solar system once, lose whatever mass it loses, experience whatever fragmentation it experiences, and then depart, climbing back out toward the stars. The fragments, if they survive, will also depart, each on its own slightly different trajectory, dispersing slowly as they recede from the sun. In a few years, they will be too faint to detect. In a few decades, they will be beyond the orbit of Neptune, cooling and darkening. In a few centuries, they will be back in interstellar space, frozen again, inert again, carrying with them the scars of this brief encounter with light and warmth. The particles that leave the comet, dust grains shed from the nucleus, carried away by the expanding gas, pushed outward by radiation pressure, do not vanish. They enter independent orbits around the sun, each grain following a trajectory determined by its size, mass, and the balance of forces acting on it. The smallest grains, submicron particles with high beta values, are accelerated to velocities exceeding the escape velocity from the solar system. They leave on hyperbolic paths, joining the population of interstellar dust grains that drift through the galaxy. Larger grains, with beta values less than 1, remain gravitationally bound and enter elliptical orbits that may persist for thousands or millions of years. These orbits are not random. They cluster near the orbit of the comet, forming a stream of debris that extends along the comet's path through the solar system. The stream is narrow near the comet, where particles have been recently ejected and have not yet dispersed, but it broadens with time as particles with slightly different velocities and beta values drift apart. The dispersal is slow, centimeters or meters per second of relative velocity, but over years and decades, it spreads the stream across a wide region of space. Eventually, the stream may disperse entirely, the particles mixing with the background population of interplanetary dust, losing their association with the parent comet. For comets on periodic orbits, those that return to the inner solar system repeatedly, the dust streams can become dense and well-defined, filled with particles ejected over many apparitions. Earth's orbit intersects several such streams, and when Earth passes through one, the particles enter the atmosphere at high velocity and burn up, creating meteors. The annual meteor showers, Perseids in August, Leonids in November, Geminids in December, are caused by Earth encountering these streams. The timing of each shower is predictable because Earth's orbit and the location of the stream are both stable over human timescales. For 3I/Atlas, the situation is different. The comet's hyperbolic orbit does not intersect Earth's orbit, so the dust stream it creates will not produce meteors visible from Earth. The particles, once shed, will follow their own elliptical orbits, each slightly different depending on when and where the particle was ejected. Some particles, released before perihelion when the comet was still approaching the Sun, will have orbits with perihelia inside the comet's perihelion distance. Others, released after perihelion, will have perihelia outside the comet's perihelion distance. The collection of all these orbits forms a toroidal structure, a donut-shaped region of enhanced dust density centered on the comet's orbit. The particles are small but numerous. Over the course of its passage through the inner solar system, 3I/Atlas may shed billions or trillions of individual grains with a total mass of several million kilograms. The grains are distributed across a volume of space that, within a few years, will span millions of kilometers along the comet's orbit. The density is low, perhaps 1 grain per cubic kilometer, or even less, but the total number is large. These grains will remain in the solar system indefinitely, slowly spreading out and mixing with the background dust population. Some of the larger particles, millimeter-sized grains and pebbles, will eventually cross the orbits of planets. A particle on an orbit that crosses Earth's orbit may, millions of years hence, encounter Earth and enter the atmosphere. The particle will burn up, creating a sporadic meteor, a shooting star unassociated with any known meteor shower, appearing at a random time and location. The meteor will be brief, lasting only a fraction of a second, and it will carry no information about its origin. But it will be a remnant of 3I/Atlas, a fragment of an interstellar comet that passed through the solar system in the early 21st century and left behind a trail of debris. The dust also contributes to the zodiacal light, a faint glow visible in the night sky along the ecliptic, the plane of Earth's orbit, and the orbits of the other planets. The zodiacal light is caused by sunlight scattered by interplanetary dust, the collective glow of countless particles in orbit around the Sun. The dust comes from many sources: asteroids, comets, collisions, the slow grinding down of larger bodies, and it is constantly replenished as new particles are added and old particles are lost to collisions. Radiation pressure, and the Poynting-Robertson effect, a subtle drag force caused by the fact that absorbed and re-emitted photons carry away orbital angular momentum. The Poynting-Robertson effect causes dust particles to spiral slowly inward toward the Sun. The effect is weak. It takes thousands or millions of years for a particle to spiral from the orbit of Earth to the Sun, but it is inexorable. Particles that are not removed by other processes, collisions, ejection by radiation pressure, encounters with planets, will eventually fall into the Sun and be vaporized. The time scale depends on the particle size, with smaller particles spiraling inward faster than larger ones. For a micron-sized grain at Earth's orbital distance, the Poynting-Robertson lifetime is roughly 10,000 years. For a millimeter-sized grain, it is 10 million years. The dust from 3I/Atlas will experience this same slow spiral. The particles, once in orbit, will gradually lose angular momentum and drift inward. Some will be perturbed by gravitational encounters with planets, altered onto new orbits that may eject them from the solar system or send them into the Sun more quickly. Others will collide with existing dust particles or with meteoroids, shattering into smaller fragments or merging to form larger agglomerates. A few may eventually impact a planet or a moon, adding a tiny increment to the mass of that body and perhaps in the distant future, being sampled by a geologist or a rover and identified by its chemical or isotopic composition as having come from an interstellar comet. The trail of debris is the comet's legacy, the material remnant of its passage that will outlast the comet itself, long after the nucleus has fragmented and disintegrated, or receded beyond detection into the outer solar system and interstellar space. The dust will remain, orbiting the sun, scattering light, occasionally burning as meteors. The particles are anonymous, indistinguishable from the countless other dust grains that fill the solar system, but they are there, carrying within their mineral grains and organic molecules the chemical fingerprints of another star's planetary system. Only took a few weeks of sunlight to spread 1 million kilograms across the solar system. Some of the dust may eventually leave the solar system entirely, not because of radiation pressure, but because of gravitational encounters with planets, particularly Jupiter. A particle on an orbit that passes close to Jupiter can be gravitationally scattered, its velocity increased or decreased depending on the geometry of the encounter. If the velocity increase is large enough, the particle can be ejected onto a hyperbolic trajectory, escaping the solar system and entering interstellar space. This process is rare for any individual particle, but given the large number of particles and the long timescales involved, some fraction of the dust from 3I/Atlas will eventually be ejected. Completing a cycle, interstellar comet arrives, sheds dust, dust is ejected, returning to interstellar space from which the comet came. The dust grains that escape carry with them a sample of the comet's composition, albeit heavily processed by solar heating and radiation. The grains will travel through the galaxy at velocities of tens of kilometers per second, eventually joining the general population of interstellar dust. They may pass close to other stars, be heated again, sublimate again, or be incorporated into new molecular clouds where future stars and planets will form. In this way, the material of comets, both interstellar and solar system in origin, circulates through the galaxy, mixing and cycling through different environments over billions of years. The meteor showers that might have been, had the orbit been different, had the trajectory intersected Earth's path, will not occur. But the dust remains, a dispersing cloud of particles that will orbit the sun for millennia, a faint and invisible monument to the comet's passage. The particles will never be recovered, never be analyzed in a laboratory, never reveal their secrets beyond what can be inferred from distant observations. They will simply orbit, slowly spiraling inward, slowly dispersing, until they are gone, vaporized in the sun, ejected by Jupiter, or lost to collisions. The comet's legacy, like the comet itself, is transient. The return journey, if it can be called that, begins at perihelion. The moment the comet reaches its closest approach to the sun, the inward component of its velocity becomes zero, and the outward component begins to dominate. The comet's velocity vector, which has been pointing more and more directly toward the sun as it falls inward, rotates through 90 degrees and begins pointing away. The speed at perihelion is at its maximum, several tens of kilometers per second, but this speed is now directed outward, carrying the comet away from the sun on the outbound leg of its hyperbolic trajectory. The recession is at first imperceptible. The comet's distance from the sun increases slowly, only a few million kilometers per day, and the solar flux decreases correspondingly. The surface temperature begins to drop, but the change is gradual, at 0. 6 astronomical units. The solar constant is roughly 3,800 watts per square meter. At 0.7 AU, a week or two after perihelion, it is 3,200 watts per square meter. Still intense. Still more than twice the flux at Earth's orbit. The sublimation continues. The coma persists. The tails remain visible. For a casual observer, the comet appears almost unchanged, still bright, still active, still surrounded by its glowing cloud of gas and dust. But the activity is declining. The outgassing rate, which peaked at perihelion, begins to decrease as the surface cools. The coma, no longer replenished at the same rate, starts to shrink. The plasma tail, dependent on the continuous production of ionized gas, becomes fainter and shorter. The dust tail, fed by particles already in flight, remains visible for longer, but it too begins to fade as the dust disperses and the production of new particles slows. The comet is dimming, not dramatically, but measurably, a few percent per day at first, then more as the distance increases and the solar flux continues to drop. The fragments, if they survived perihelion, are also receding, each on its own slightly different trajectory. The differences are small, only a few tens or hundreds of meters per second in velocity, corresponding to slightly different perihelion distances or slightly different timings of the perihelion passage, but over weeks and months. These small differences accumulate into large separations. Fragment A, the largest and brightest, may be ahead of or behind Fragment B by thousands or tens of thousands of kilometers, and the gap continues to grow. The fragments are no longer a coherent group, but a dispersing cluster, each fading independently as it climbs out of the inner solar system. The orbit, altered by the non-gravitational forces during the approach and perihelion passage, is now slightly different from the orbit that was predicted based on early observations. The perihelion distance may be a few thousand kilometers larger or smaller. The velocity at perihelion may be a few meters per second higher or lower. The orbital plane may be tilted by a fraction of a degree. These changes, though small, are permanent. They reflect the cumulative effect of all the outgassing that occurred from the time the comet became active until the time it passed perihelion and began to recede. The new orbit is still hyperbolic. The non-gravitational forces, though they altered the trajectory, were not strong enough to change the eccentricity significantly. The comet remains on an escape trajectory, bound for interstellar space. The velocity at infinity, the speed the comet will have once it is far from the Sun and the Sun's gravitational influence has become negligible, is roughly the same as it was on arrival, perhaps slightly higher or lower depending on the net effect of the non-gravitational forces. The comet will leave the solar system at a speed of roughly 26 kilometers per second, traveling in a direction determined by the deflection caused by the Sun's gravity and the small perturbations from non-gravitational forces and planetary encounters. The direction of departure is different from the direction of arrival. The Sun's gravity has bent the comet's trajectory, rotating it through an angle of perhaps 30 or 40 degrees, depending on the perihelion distance and the velocity. This gravitational slingshot effect is the same mechanism used by spacecraft to gain energy from planetary flybys. The comet, though it loses energy to sublimation and the rocket effect, still gains a net change in velocity direction from the gravitational encounter. It leaves the solar system on a path that is different from the path on which it arrived, heading toward a different region of the galaxy, toward stars it would not otherwise have encountered. The comet crosses Earth's orbit again, but on the outbound leg, and at a different location, the ascending or descending node, depending on the inclination and the direction of motion. Earth is not nearby. The crossing occurs when Earth is on the opposite side of its orbit, tens of millions of kilometers away. There is no close encounter, no opportunity for detailed observations. The comet simply passes through the plane of Earth's orbit and continues outward, climbing toward the orbit of Mars, then the asteroid belt, then Jupiter. The brightness continues to decline. By the time the comet reaches the orbit of Mars, a few weeks or months after perihelion, it has faded by a magnitude or more. The coma is smaller, the tails shorter and fainter. The plasma tail may have disappeared entirely, the ionization rate having dropped below the threshold needed to produce visible emission. The dust tail lingers, sustained by particles that are still in flight, but it is dispersing, spreading out, becoming more diffuse and harder to detect against the background sky. Observations become more difficult. The comet is now faint, requiring larger telescopes and longer exposures. The number of observers tracking it declines as the comet fades below the detection limit of smaller instruments. Professional observatories continue to monitor it, but the cadence of observations decreases, once per week instead of nightly, once per month as the comet continues to fade. The data becomes sparser, the orbit determination less precise. The uncertainties grow. By the time the comet reaches the orbit of Jupiter, roughly a year after perihelion, it is very faint, magnitude 15 or fainter, visible only in large telescopes under excellent conditions. The coma is barely detectable, a faint haze around the nucleus. The tails are gone. The outgassing has nearly ceased, the surface having cooled to the point where even the most volatile ices sublimate only slowly. The comet is transitioning back to an inert state, reverting to the cold, dark object it was before it entered the inner solar system. Only took a year to fade back into the darkness from which it came. The recession continues, relentless, the distance increasing by millions of kilometers per day as the comet's velocity carries it outward. The Sun, which dominated the sky during perihelion, is now one bright star among many, its disk too small to resolve without magnification. The solar flux is a small fraction of what it was at perihelion, at Jupiter's orbital distance. It is only 4% of the flux at Earth's orbit, and declining as the inverse square of the distance. The surface temperature drops below the sublimation point of water ice, then carbon dioxide ice, then carbon monoxide ice. The comet is freezing again, molecule by molecule. The last traces of outgassing ceasing as the warmth dissipates, there will be no return. The hyperbolic orbit, unyielding, carries the comet outward past Saturn, past Uranus, past Neptune. At each planetary orbit, the Sun is dimmer, the solar flux weaker, the warmth more faint and distant. The comet crosses the heliopause, the boundary where the solar wind gives way to the interstellar medium. Though there is no marker, no change in appearance, nothing to indicate that the solar system has been left behind, the comet simply continues, coasting on the velocity it gained from the Sun's gravity and retained despite the mass loss and non-gravitational forces. In a few decades, the comet will be beyond the Kuiper belt. In a century, it will be farther from the Sun than any solar system object except the most distant Oort cloud members. In a millennium, it will be light years away, traveling through the space between stars. Once again, an interstellar object, indistinguishable from the countless other comets and planetesimals that drift through the galaxy. The encounter with the Sun will be a brief episode in its history, a few months of warmth and light bookended by eons of cold and darkness. What has been learned from the delay? From the hours-long discrepancy between prediction and observation, from the slow recalculation of the orbit, from the accumulation of data points that revealed the presence of non-gravitational forces, extends beyond this single comet. Every active comet teaches lessons about the behavior of ice in space, about the response of small bodies to solar heating, about the interplay of forces that govern orbital evolution. But 3I/Atlas, as an interstellar visitor, offers something more, a comparative data point, a sample from outside the solar system that can be measured against the known population of solar system comets to test whether the physics is universal or whether differences exist. The delay itself quantifies the comet's activity level. By measuring how much the arrival time shifted, and by modeling the non-gravitational forces required to produce that shift. Planetary scientists can estimate the mass loss rate, the active fraction of the surface, and the magnitude of the rocket effect. These quantities, in turn, constrain the composition and structure of the nucleus. A larger delay implies higher activity, more outgassing, more thrust. A smaller delay implies less activity, a more dust-covered surface, weaker forces. For 3I/Atlas, the delay of several hours suggests moderate activity, neither exceptionally vigorous nor unusually weak, consistent with a nucleus that has a mixed surface of exposed ice and dust-covered regions. The outgassing pattern inferred from the direction of the non-gravitational force provides clues about the distribution of active areas on the nucleus. The fact that the force is retrograde, opposing the orbital motion, implies that the active areas are oriented such that peak outgassing occurs when they face forward along the orbit. This, in turn, constrains the rotation axis and the location of the active regions. If the rotation axis were perpendicular to the orbital plane, and if the active areas were near the equator, the outgassing pattern would vary symmetrically with rotation, and the time average force might have no transverse component. But the observed retrograde force suggests a more complex geometry, with the rotation axis tilted and the active areas concentrated in specific locations that are not symmetric about the spin axis. The fragmentation, if that is what the observed multiple condensations represent, provides information about the mechanical strength of the nucleus. The fact that the nucleus split at all indicates that the cohesive forces were weak, likely only a few tens or hundreds of pascals, comparable to the tensile strength of freshly fallen snow or weakly compressed powder. This is consistent with observations of other cometary nuclei that have been imaged up close by spacecraft, which reveal surfaces that are fragile and porous, with bulk densities less than half that of solid ice. The low density implies that the nucleus is not a monolithic block, but rather a loosely consolidated aggregate of smaller pieces, a rubble pile held together by weak cohesive forces and minimal self-gravity. The rate at which the fragments separated, a few meters per second, provides a constraint on the energy of the breakup. A slow separation implies a gentle process, perhaps driven by differential outgassing or thermal stress, rather than a violent explosion. The kinetic energy of the fragments, calculated from their masses and separation velocities, is small, equivalent to the energy that would be released by sublimating only a few kilograms of ice. This suggests that the fragmentation did not require a large input of energy, only enough to overcome the weak cohesive forces holding the nucleus together. The chemical composition, as inferred from spectroscopic observations, suggests that 3I/Atlas is not dramatically different from solar system comets in its gross chemistry. Water is the dominant volatile, with carbon monoxide and carbon dioxide as secondary components. The relative abundances are within the range observed for solar system comets, though the uncertainties are large enough that subtle differences cannot be ruled out. This similarity suggests that the processes of ice formation, condensation from the gas phase in a protoplanetary disk, trapping of volatiles in amorphous ice, chemical processing by radiation and cosmic rays are broadly similar in different stellar systems, at least for systems that form stars similar to the Sun. But the similarity is not complete. There are hints, faint, tentative, buried in the noise, that some molecular abundances may differ. The ratio of carbon monoxide to water, for instance, appears slightly elevated compared to typical solar system comets. Though the measurement is near the detection limit, if this difference is real, it could reflect a colder formation environment, where carbon monoxide, being more volatile than water, is more efficiently trapped in the ice. Or it could reflect a different carbon-to-oxygen ratio in the protoplanetary disk, a consequence of the chemical composition of the molecular cloud from which the parent star formed. The isotopic ratios, which would provide the most definitive test of differences in origin, remain unmeasured. The deuterium to hydrogen ratio in water, the nitrogen isotope ratio, the oxygen isotope ratio, all are valuable diagnostics, but all require high-resolution spectroscopy and high signal-to-noise data that are beyond the reach of current observations of this faint comet. Future observations. Perhaps with next-generation telescopes or with spacecraft missions, might obtain these measurements for other interstellar comets, but for 3 I/Atlas, the question remains open. The orbit determination, refined over weeks and months of observations, provides a precise trajectory that can be extrapolated backward in time to estimate where the comet came from. The calculation is not simple. The comet's motion through the galaxy is affected by the gravitational field of the Milky Way, by encounters with molecular clouds and spiral density waves, by the slow perturbations caused by passing stars. Tracing the orbit backward more than a few million years becomes increasingly uncertain, as small errors in the initial velocity and position amplify into large uncertainties in the past trajectory, but rough estimates can be made. The comet likely originated within a few parsecs of the Sun, ejected from a planetary system belonging to a star that is now perhaps 10 or 20 light-years away, possibly more. The exact star cannot be identified because the comet's trajectory does not point back to any single stellar system with sufficient precision. The uncertainties are too large, but the general direction can be determined, and it points toward a region of the sky where several Sun-like stars exist, any of which could be the comet's parent star. Or perhaps the parent star is too faint to be catalogued or has moved significantly since the comet was ejected, or no longer exists. Having evolved off the main sequence or been disrupted in a stellar encounter, the velocity at infinity, measured at roughly 26 kilometers per second, is consistent with ejection from a star moving with a similar galactic orbit to the Sun's. Stars in the solar neighborhood orbit the galactic center at speeds of around 200 kilometers per second, with random velocities of a few tens of kilometers per second superimposed on this orderly rotation. A relative velocity of 26 kilometers per second suggests that the parent star is part of the same general stellar population as the Sun, not a high-velocity star from the galactic halo, not a member of a distant stellar stream or cluster, but an ordinary disk star, probably similar in age and composition to the Sun itself. The time since ejection is more difficult to estimate. If the comet has been traveling at its current velocity for the entire time since ejection, and if it originated 10 light-years away, the travel time would be roughly 100,000 years, but this assumes straight-line motion, which is only approximately correct. The comet's trajectory through the galaxy is curved by the galactic gravitational field, and encounters with molecular clouds or close passes by other stars could have altered the velocity. The true travel time could be longer, hundreds of thousands of years, perhaps 1,000,000 years or more, if the comet's path was more circuitous or if it spent time in regions of lower velocity. What has been learned, ultimately, is that interstellar comets exist, that they can be detected and studied when they pass through the solar system, and that they are, in many respects, similar to solar system comets. They are made of ice and dust. They sublimate when heated by the sun. They produce comet and tails. They fragment under thermal stress. They exhibit non-gravitational forces. The physics is the same. The chemistry appears broadly similar. Though subtle differences may exist, the behavior is predictable, within limits, using the same models and techniques that are applied to solar system comets. But interstellar comets also carry uncertainties that cannot be resolved with current observational techniques. Their origins remain mysterious. Their exact compositions remain unknown. Their interior structures remain hidden, and their histories, where they formed, how they were ejected, what they encountered during their journey through interstellar space, are recorded only in chemical and isotopic signatures that are too faint to measure from Earth-based telescopes. To truly understand these visitors, To unlock the information they carry about other stellar systems and the diversity of planetary formation processes would require close-up observations, spacecraft missions, sample returns, detailed in situ measurements of the kind that have been performed on only a handful of solar system comets. Only took one interstellar visitor to realize how much there is still to learn. The delay also serves as a reminder of the limits of prediction. Orbital mechanics is precise for inert bodies, for asteroids and planets that follow purely gravitational trajectories, but for active comets, prediction is approximate. The non-gravitational forces introduce uncertainties that grow over time, and the further in advance one tries to predict a comet's position, the larger the uncertainties become. For short-term predictions, days or weeks, the uncertainties are small, manageable, acceptable. For long-term predictions, months or years, the uncertainties grow, and the predicted orbit becomes more of a probability distribution than a single trajectory. This has practical implications for future observations and for planning spacecraft missions. If another interstellar comet is detected far from the Sun, early enough that a spacecraft could be launched to intercept it, the orbit determination must be precise enough to ensure the spacecraft arrives at the right place at the right time. But if the comet is active, the non-gravitational forces will alter the orbit in ways that cannot be predicted exactly in advance. The spacecraft's trajectory must be flexible, capable of adjusting to updated orbit determinations as new observations refine the target's position. The mission design must account for uncertainties, for contingencies, for the possibility that the comet will not be exactly where the early predictions suggested. For 3I/Atlas, no spacecraft was launched. The comet was discovered too late. Its interstellar origin recognized too late. For any mission to be planned and executed in time, the opportunity was missed. But the lessons learned from this comet about activity levels, about non-gravitational forces, about fragmentation and chemical composition will inform the planning for future missions. Whenever the next interstellar visitor is detected, the delay, the hours-long discrepancy between prediction and observation, is part of the data, part of the story, part of what this comet has taught about the behavior of ice in space. The comet does not know it has taught anything. It simply continues its recession, climbing outward through the solar system, shedding mass, fragmenting or remaining intact, following the trajectory that was written by the Sun's gravity and altered by its own sublimation. The lessons are human constructs, interpretations of observations, models fitted to data, papers written and published in journals that the comet will never read. But the lessons are real. They expand the understanding of how comets behave, how ice responds to sunlight, how small forces accumulate to produce measurable effects. And the delay remains in the record, a permanent marker in the orbital data, a timestamp that is hours late, a small but significant discrepancy that tells of ice transforming to gas, of gas escaping into space, of a comet that arrived when it arrived, not when the mathematics said it should. The comet is already gone, in a sense, though it remains visible in large telescopes and continues to be tracked by a dwindling number of observers. Already gone in the sense that it has passed perihelion, completed its close approach, begun its recession. Already gone in the sense that the peak brightness has faded, the tails have dispersed, the coma has shrunk to a faint glow around an invisible nucleus. Already gone in the sense that the opportunity for detailed study has passed. The best observing conditions are over. The most intense activity has ceased. What remains is the long, slow fade, the gradual dimming as the comet climbs outward, the decline in brightness that will continue for months and years until the comet is too faint to detect even with the largest telescopes. By the time the comet crosses the orbit of Jupiter, more than a year after perihelion, it is fainter than magnitude 16. beyond the reach of all but the largest professional instruments. The observations are infrequent now, perhaps one set of images per month, obtained during dedicated observing runs when telescope time can be allocated to tracking a fading object of scientific interest but limited immediate importance. The orbit determination continues to be updated, but the updates are minor, refining the trajectory by smaller and smaller amounts as the non-gravitational forces become negligible and the comet's motion becomes dominated once again by gravity alone. The coma is barely visible, a diffuse haze only a few thousand kilometers across, much smaller than it was at perihelion when it spanned hundreds of thousands of kilometers. The outgassing has nearly ceased. The surface temperature, now far below the sublimation point of water ice, is too low to drive significant activity. Only the most volatile ices, carbon monoxide, if any remains, might still be sublimating, releasing trace amounts of gas at rates too low to produce a detectable coma in all but the most sensitive observations. The nucleus is reverting to its dormant state, the state it was in during its millions of years of interstellar travel, the state it will return to as it departs the solar system and resumes its journey through the galaxy. The fragments, if they survived, are dispersing. The separation between them has grown to tens of thousands of kilometers, perhaps more, and continues to increase at a few meters per second. Each fragment is now too faint to be detected individually. What observers see, if they see anything at all, is a combined signal, a single faint point of light that might be one fragment or several, indistinguishable at this distance and brightness level. The question of whether the nucleus fragmented or remained intact cannot be definitively answered from the available data. The observations are too sparse, the signal too weak, the uncertainties too large. By the time the comet reaches the orbit of Saturn, roughly 2 years after perihelion, it has faded beyond the detection limit of most telescopes. Only the very largest instruments, using long exposures and sensitive detectors, can still detect it. And even then, the signal is marginal, a few photons per hour, barely distinguishable from the background noise. The last observations are made, the positions measured and reported, and then the comet fades into invisibility. It continues to exist, continues to move outward, but it is no longer detectable. It has become, once again, a dark object traveling through space, visible only to hypothetical instruments that do not yet exist or to spacecraft that will never be built. The orbit, extrapolated from the last observations, predicts the comet's future trajectory with reasonable accuracy. It will cross the orbit of Uranus in another few years, Neptune a few years after that. It will reach the heliopause, the boundary between the solar wind and the interstellar medium, in a few decades. It will be a light year from the Sun in roughly 10,000 years, 2 light years in 20,000 years. The predictions become more uncertain the farther into the future they are extrapolated, as small uncertainties in the velocity and direction accumulate into large uncertainties in the position. But the general trajectory is clear, outward, away from the Sun, toward the stars. The comet will not encounter another star for a very long time. The nearest stars are several light years away, and the comet's velocity is only 26 kilometers per second, roughly 1/10,000th the speed of light. At this speed, it will take tens of thousands of years to cover the distance to the nearest stars, and there is no guarantee that its trajectory will bring it close to any of them. Space is vast, and the distances between stars are immense. The comet might travel for hundreds of thousands of years, or millions, before it happens to pass close enough to another star to be perturbed onto a new trajectory or captured into a new stellar system. Or it might never encounter another star. It might drift through the galaxy indefinitely, one small frozen body among trillions, never again experiencing the warmth of a close stellar passage, never again developing a coma or tails, never again shedding mass to sublimation. It would remain frozen, Inert, invisible, a silent traveler through the dark, carrying within its ice and dust the chemical fingerprints of the star system where it formed, the record of its brief encounter with the sun, and the scars of solar heating that altered its surface and depleted its volatile ices. The sun, from the comet's perspective, is now just another star, brighter than most, but no longer dominant, no longer a source of warmth. At the orbit of Saturn, the sun is a brilliant point of light, still far brighter than any other star, but small enough that its disk cannot be resolved without magnification. At the orbit of Neptune, the sun is brighter than the full moon as seen from Earth, but it is no longer overwhelming. Beyond the heliopause, in the outer reaches of the Oort cloud, the sun is simply the brightest star in the sky, distinguishable from other stars only by its brightness, not by any heat or influence it exerts. And beyond that, in true interstellar space, the sun is one star among billions, indistinguishable to the comet from any other G-type star in the galactic disk. The comet has no eyes, no instruments, no awareness. It does not know that it has left the solar system. It does not remember the warmth, the light, the brief months of activity. It simply exists, tumbling slowly through the void, cold and dark, its surface temperature equilibrated with the cosmic microwave background and the faint starlight of the Milky Way. Only took a few months of warmth to spend eons in the cold again. The data remain. The observations, collected over months, are archived in databases and repositories where they can be accessed by researchers for decades or centuries to come. The orbital elements, refined through hundreds of position measurements, are recorded with their uncertainties and published in journals and catalogs. The spectroscopic data, showing the emission lines of water vapor and carbon monoxide and cyanogen, are preserved in digital form, available for reanalysis as new techniques and models are developed. The light curves, tracking the comet's brightness from first detection to final observation, are plotted and stored, documenting the rise and fall of activity as the comet approached and receded from the sun. The images, too, are preserved, photographs showing the faint smudge of the coma, the elongated dust tail, the subtle structures within the plasma tail. These images, captured by telescopes around the world, are snapshots of a moment in the comet's history, frozen in pixels and stored on servers. Future researchers might examine them, searching for details that were overlooked in the initial analysis, or comparing them to images of other comets to identify common patterns or unique features. The comet itself has moved on, beyond observation, beyond reach. But its passage through the solar system has left a mark, not a physical mark, not a scar on any planet or moon, but a mark in the scientific record. A data set that documents the encounter and provides a reference point for future studies of interstellar objects. The comet was here. It was observed. It was measured. And then it left. The next interstellar comet, whenever it arrives, will be compared to this one. Astronomers will ask, is it similar? Does it show the same activity levels? The same chemical composition? The same behavior under solar heating? Or is it different, reflecting a different origin, a different stellar environment, a different history? Each interstellar visitor adds to the sample, expands the understanding, tests the hypothesis that comets are universal, that the physics and chemistry of ice formation are the same everywhere. But for now, there is only 3 I/Atlas, and 1 I/Oumuamua before it, and 2 I/Borisov, and whatever few other interstellar objects have been detected and characterized. The sample is small. The statistics are poor. The conclusions are tentative. More visitors are expected. Models predict that several interstellar objects should pass through the inner solar system each year, though most are too faint to detect with current surveys. As telescopes improve and surveys become more sensitive, more of these visitors will be found, observed, and studied, and each will carry with it the same questions. Where did it come from? How long has it been traveling? What is it made of? How does it compare to solar system objects? And each will, for a brief time, be visible, measurable, knowable, before it fades into the distance and is lost again to the darkness, carrying its secrets back into the galaxy from which it came. The comet does not know it is leaving. It does not know it was observed. It simply continues its motion, governed by the laws of physics that apply equally in the solar system and in the space between stars. It falls away from the sun, climbs the gentle slope of the gravitational well, and eventually, imperceptibly, transitions from bound to unbound. From solar system object to interstellar traveler, the transition is gradual, unmarked, unremarkable. There is no boundary, no sign, no moment when the solar system ends and interstellar space begins. Just distance, increasing, and velocity, unchanging, carrying the comet outward into the galaxy's rotating disk. Already gone, though still moving, already invisible, though still there, already beyond reach. Though the data remain, the record persists, the observations archived. The comet is history now, a past event, a completed encounter. One more visitor from beyond that came, was seen, and departed, leaving behind only numbers and images and the quiet knowledge that the galaxy is full of such travelers, most of them unseen, most of them unknown, drifting through the dark spaces between the stars. The sun is now a star among stars, no brighter than Sirius as seen from Earth, and fading. The comet moves through a darkness that is not quite absolute. The Milky Way provides a faint glow, a soft wash of light from billions of distant stars, but it is a darkness that will deepen as the comet recedes, as the sun fades to the brightness of Canopus, then Vega, then Arcturus, then becomes indistinguishable from the background stellar population. The motion continues but becomes meaningless. There is no reference frame here, no fixed points by which to measure progress. The comet moves at 26 kilometers per second relative to the sun, but relative to the local interstellar medium, relative to the slowly rotating disk of the galaxy. The velocity is different, sometimes faster, sometimes slower, depending on the direction and the local motion of gas and stars. The temperature is uniform now. The surface, the interior, the ice, the dust, all have equilibrated to the ambient temperature of space, perhaps 3 Kelvin, the temperature of the cosmic microwave background plus a tiny contribution from starlight. At this temperature, even hydrogen would be solid if pressure allowed it. Molecular motion has nearly ceased. Atoms vibrate in their lattices with the minimum energy permitted by quantum mechanics. There is no sublimation, no activity, no change. The comet is as inert as matter can be, frozen in a configuration that may persist for billions of years. Time itself seems to slow, though of course it does not. The galaxy rotates, the comet moves. Stars are born and die. Molecular clouds collapse and disperse. Spiral arms sweep past and fade. But on the scale of the comet, on the time scale of ice and dust and silence, nothing happens. Days are indistinguishable from years. Years are indistinguishable from millennia. The comet tumbles slowly. Its rotation period perhaps still 8 hours, perhaps altered slightly by the torques exerted during perihelion when outgassing was asymmetric. But there is no way to measure the rotation here, no observer, no change in illumination to mark the passage of time. The stars drift past, or the comet drifts past the stars. The distinction is meaningless. The constellation patterns, as seen from the comet's perspective, shift slowly as the viewing angle changes. Stars that were ahead are now behind. Stars that were faint grow brighter as the distance decreases. Others fade as they recede. but the changes are imperceptible on human timescales. Centuries must pass before the sky from the comet's vantage point appears noticeably different. The galaxy itself is a quiet place, emptier than can be easily comprehended. The average distance between stars in the solar neighborhood is a few light years, roughly a parsec, which means that the typical volume occupied by a single star and its retinue of planets and comets is a sphere millions of times the diameter of the solar system. Most of that volume is empty. No planets, no comets, no dust, just vacuum, or near vacuum, with perhaps one hydrogen atom per cubic centimeter, sometimes more in molecular clouds, sometimes less in the voids between spiral arms. The comet is one small object in this vast emptiness. Its cross-sectional area is perhaps 10 square kilometers. The cross-sectional area of the galaxy is trillions of square light-years. The probability that the comet will collide with anything, a star, a planet, another comet, even a dust grain over the next million years is vanishingly small. It will simply drift, unperturbed, alone, silent. There is no sound. Of course, sound requires a medium, and there is no medium here. The interstellar gas is too tenuous to carry acoustic waves. Even if there were sound, there is nothing to generate it, no sublimation, no outgassing, no movement of material across the surface. The comet is silent. The space around it is silent. The galaxy, for all its grandeur, is silent. The light from distant stars falls on the comet's surface, a few photons per second per square meter, absorbed and re-emitted as infrared radiation so faint it would be undetectable even with the most sensitive instruments. The energy balance is perfect. Absorbed energy equals emitted energy, and the temperature remains constant. There is no day, no night, no cycle of heating and cooling, just equilibrium, unchanging, eternal. And the comet drifts, outward from the sun, though the sun is no longer relevant, inward towards some stars, outward from others. The directions arbitrary. Through the spiral arm, or between spiral arms, the distinction unclear. The motion is real, but it signifies nothing. The comet does not arrive anywhere. It does not depart from anywhere. It simply is, somewhere in the galaxy, moving, existing, silent. Time passes, years, centuries, millennia. The sun continues its own orbit around the galactic center, completing a circuit every 230 million years. The comet's galactic orbit is different, slightly faster or slower, slightly more or less eccentric. Over millions of years, the comet and the sun drift apart, their galactic paths diverging. Eventually, after tens or hundreds of millions of years, they will be on opposite sides of the galaxy, separated by 50,000 light-years, with no possibility of reunion, but that is time so distant it loses meaning. For now, though now is also meaningless here, the comet simply drifts through the dark, cold and silent, unchanged and unchanging. A grain of ice and dust carrying within it the memory, recorded in isotopes and chemistry and structure, of a star that formed it, a journey through interstellar space, a brief encounter with warmth and light, and a return to the cold from which it came and to which it belongs. The silence deepens, the darkness deepens, the motion continues, imperceptible, eternal, and the comet, already gone, already invisible, already beyond all reach and all knowing, drifts on.